So welcome everybody to this new day, last day of ChemReactor. We already reached to the last day. So today we start a bit later for us in Europe. It's not that early anymore. So I hope you can enjoy the day. And we will start today with a great session on advances in chemical reactor fundamental. We have several speakers and interesting presentation today. So I would wait another 2 minutes until 10 to start the session so that everybody can join properly and follow the presentations from the beginning. So I think all the speakers are already here. So I will start introducing the first speaker. That is Professor Christophe Vial from the Institut Pascal in Clermont-Ferrand, France. And he will introduce us to the development of a multi-particle optical trajectography technique for the hydrodynamic analysis of a stirred tank devoted to dark fermentation. So it's almost 10, and I would like to give you the word, Professor Vial, for this, for sure, interesting presentation. I cannot hear you. No, not yet. I don't know if... Do you all have this problem hearing Professor Vial? Perfect.
Okay,
very
but,
good.
yes, but I cannot share my presentation.
Ah, okay, not yet. So what is going on with the...
I'm not allowed to share.
Okay.
Thanks a lot. It's working now. Okay.
Perfect. So free way for your presentation. Thank you.
Okay. You can see the slide. Okay.
Yes, all good now.
Very good.
Perfect.
Okay. So so my presentation is entitled Development of a Multi-Particle Optical Trajectography Technique, as it was told. This work has been carried out in Institut Pascal, which is a French laboratory situated in Clermont-Ferrand in the center of France, as you can see on the map. This work has been carried out by the chemical engineering group, but in collaboration with the vision group of the lab. Let's start with the outline of my speech now. I will first introduce the context and the background of this work, and especially the objectives with a link to dark fermentation. I will try to explain you rapidly the why, which shows the trajectography method and the materials which are necessary. In the results, I will display the validation of the method and some key results before concluding. So let's start with the context, and the context is in relation to energy transition, because dark fermentation is a biochemical process which is able to produce second generation biohydrogen using as the substrate lignocellulosic biomass, I mean food and agro wastes, for example. It is an anaerobic consortium of microorganisms, and as a result, you obtain a biogas enriched in biohydrogen. And even if we have CO2 in this biogas, most of the carbon is recovered in the liquid phase in the form of short-chain fatty acids, usually denoted volatile fatty acids. So this is carried out in a bioreactor, usually a stirred tank. The mechanism, I will be very short, the mechanism is similar, if you know it, to that of anaerobic digestion, except that in anaerobic digestion, we have 4 steps: the hydrolysis of the biomass, the conversion to short-chain fatty acids, CO2 and H2, and at the end, these are converted by methanogens in methane. The difference here is that we suppressed the methanogens in the consortium, so we stop at the end of the 3rd step. And at the end, we have this biogas, which contains mainly biohydrogen without methane. The advantage is that it is quite faster. The 4 first steps are very faster, far faster than the methanogenesis. The advantage, in addition to this fast kinetics, is that it gives biohydrogen, of course, and biohydrogen, you all know that it is very interesting now, maybe in the future for cars. It is sustainable, and it can be used in conjunction and complementary to a lot of other processes that are able to give hydrogen, to provide power. It can be also a first step of anaerobic digestion. We have projects on this point to have enhanced anaerobic digestion with higher methane yields, or you can have bioplastic, biodiesel, and so on. So it is, in fact, what we call a building block of the biorefinery, the future biorefinery that we could use to make biomass and bioenergy at the same time. Of course, it has some drawbacks, and it is strongly dependent on the pH, on the composition of the effluent, and also the partial pressure of biohydrogen, which is self-inhibiting. And what we have shown in previous results is that it is also very sensitive to mixing. If you increase too much rotation speed and, in fact, the mechanical stress on the microorganism, you have a decrease on hydrogen yield and the volume of hydrogen produced, because these experiments were carried out in batch. So this was published in the previous work, and so we have an interest in better describing the hydrodynamics and the quality of mixing in the stirred tank bioreactor. Of course, this means that we operate at very low speed in comparison to what is commonly used in aerobic fermentation. I mean that we will work at low Reynolds number, because we must be at the limit of fully established turbulent regime. So now, what is the objective of our work in general? Of course, it's to maximize biohydrogen productivity, but in the present work is to try to better describe the hydrodynamic field and the hydrodynamic features of our bioreactor in the conditions which are not completely laminar, but not fully turbulent, which have not been fully explored in the literature. What are the materials we have? It's, of course, a bioreactor, and we have several sizes, but at the moment, with several scales, but at the moment, I will present results in a 2-liter bioreactor, which is mechanically stirred with a double-stage Rushton turbine. The results I will present will be with water, because the model reaction is water plus glucose, but we have also more viscous model fluids to represent the real culture medium, but I will not present them in this work. We have also particle image velocimetry, which is a good technique, but the problem is that we have only the velocities in plane. And what we would like with the method we develop is to have the 3D distribution of velocity and, if possible, of fluctuations in the reactor. We also have CFD to try to predict these features, but the problem is that with CFD is that with turbulence model and turbulence closure, this closure is not really adapted to the condition lower than to Reynolds number lower than 10,000. So in fact, these models are very good when you have high Reynolds number, but not in the present case. So they give an approximate solution, but not an exact solution. So why did we choose finally optical trajectography? We chose optical trajectography first because we could not use another method, radioactive particle tracking. This is really interesting. You follow a radioactive particle, but of course it's very expensive and it's too dangerous for a lab of biochemical engineering. And we wanted a method able to describe the 3D. So not a method which gives only data at one point. And of course, a method which is able to work on 2 liters, but higher bioreactor, which is, for example, not possible for tomographic PIV, which works on small volume. It is very expensive. And so we have chosen optical trajectography because it is a good trade-off. It's not very expensive. You need only conventional light, no laser, and you can have a Lagrangian velocity based on the monitoring of one particle. I will summarize rapidly what is the conventional optical trajectography. You have already several theses in France, in Belgium, some papers about that, where usually you monitor the position of one particle over time, over a long time in general, using 2 cameras. This is what you will find in the literature. And then after that, from the position for the 2 camera, you reconstruct the trajectory, the position, the trajectory, the velocity field. But it is long because the particle must cross all the volume. What we propose in this work is first to improve the quality of the detection, because as you can see, we use a shadowgraphy setup, which means that when the particle is in the shadow of the axis of the starry tank, you cannot see the particle, you lose the particle, and in fact, you have only parts of trajectories. We propose to use 3 cameras to better detect the particle. And then we also propose an algorithm which is able, in fact, to estimate the position of the cameras in real time. Of course, it is the position for each camera. It's not a 3D reconstruction in real time. It's for each camera we obtain in real time. The problem of optical trajectography is that it is very long. Trajectography, you can use it, you can monitor the particle over 1 day. And of course, in an aerobic tank. And as we work at low velocity, to monitor all the reactor, it can be longer, and it was too long for us. So we have also developed an algorithm which is able to follow several particles at the same time. And this you will not find in the literature at the moment for optical trajectography. I will go a little bit faster on the method. I mean that we use stereo calibration camera, which is quite classical if you know it. And if you don't know it, there is a lot of literature about that. We use 3 USB cameras with a good resolution, 4 megapixel. And then we developed the code using a free library, OpenCV, first using Python coding, and then at the end for MATLAB offline treatment. But because when we have the 3 files corresponding to the 2D position, which are obtained online, we have, of course, a post-treatment to reconstruct the 3D trajectories, and then at the end, at each position in the tank, to obtain also the velocity in terms of the Eulerian frame. So first, we have chosen the position of the camera. Theoretically, the best position of a 3 camera was this in the middle. In fact, we had problem of calibration with that, and we have chosen to put the 3 cameras on the same side, which means that finally we can need only one light, which is a LED panel. In fact, The weakness of this position is that it's not really good. We have parts of the reactor where we can see the particles. In fact, we'll see that it's not really a problem. So I give you here the main results of validation with 1, 5, and 10 particles at the same time. Of course, with 10 particles, as you can see here, it's not exactly the same time, but the same results. You obtain far more detections in 24 hours, or 1 hour, 6 hours here, and of course, over 24 hours. This is interesting because you can see that if we increase from 5 to 10 particles, the number of detections does not increase. It means that it's not necessary to put 20 or 30 particles. Usually 5 or a little bit more are enough. What is really important is that even with 3 cameras on the same site, we detect only 3 trajectories over 24 hours with 1 particle, which means that we lost only twice the particles, which means that we can have nearly a continuous trajectory of between 5 and 10 hours without losing anytime the particle. Of course, when we have 5 particles or 10, you can see that, of course, we have particles we can cross and each other, and the algorithm consider, oh, I don't know which particle is at each position, so I will consider it is a new particle. So, in fact, we will have 2 cases. If we want to have a trajectory, to follow one trajectory, it's 1 particle may be enough, and we'll go the Lagrangian velocity of a particle, which could represent a microorganisms, with 1 particle, as you can see on this picture, over 1 day, for example. You can see that even after 5% of the events detected, even with 1 particle, the particle has visited nearly all the reactor. So we can have a statistical analysis even with 1 particle, owing to the fact that we have 3 cameras. When the number of particles increases, in fact, we play on the fact that we have several particles, more detection, but in fact, we consider that we have a lot of trajectories considered in the algorithm. Does the particle visit all the reactor? It's nearly true, but of course it depends on the velocity, because with 2 Rushton turbines, you know what we have contra-rotative cells. And the issue with 1 particle is that usually it remains trapped in one of the recirculation cell, and usually it is trapped nearly in the bottom because we start with a particle in the bottom. And the advantage of working with several particles, as you can see, is that the particles are better spread and we have a better uniformity of the spatial distribution of the particles detected with 5 or 10 particles, 1 with 1 particle. If I compare the results now with the data we had on CFD and on PIV, we can see that not only the results are good in terms of average velocity, but also in terms of the fluctuations, especially at 200 RPM, because we are at the limit of a turbulent regime and we have significant fluctuation velocities. What you can see here is, however, that with 1 particle is not enough. We need at least 5 particles. And finally, for the sake of simplicity of time, it is better to work as a trade-off with 5 particles. I can show you, because it's nearly the end, the same results with planar resolution. We can see that with 1 particle, we don't have enough events at the top. The weakness is now that we cannot detect very well close to the impeller and close to the wall. We have artifacts, as you can see, close to the impeller and close to the wall, which is due to the size of the particle. I conclude now because it's time. The method we have developed is interesting with 3 cameras because we can follow with a good accuracy 1 particle. We can obtain good data in terms of the Eulerium frame with 5 particles and extract the position in real time. We have a good agreement, and the perspective we have now, I will not discuss the aspect of biohydrogen, but a colleague of mine is now trying to do the same, not on the code on the computer, but to implement this code on smart cameras based on FPGA programming. It means that the camera will do the treatment and we will not need to transfer the data to the camera to the computer, and we'll have real time, which will allow to increase the frequency, the frame per second that we can treat. Thanks for your attention.
Perfect. Thank you for the nice and clear presentation. Now we are open for questions. Of course, you can open your camera or raise your hand if you want to make any question on this presentation. I have just one point that maybe I didn't get properly. Can you please elaborate a bit more on what is the actual basis for having this optimal Reynolds number in the production of biohydrogen?
Okay, so in the previous work, yes, I come here. No, yes, we have published a series of batch experiments in which we have modified the viscosity using polyalkylene glucose with the same mixture, with the same substrate, I mean 20 grams per liter glucose. We have shown, of course, that the polyalkylene glucose were not consumed by the microorganisms, or were not toxic for the microorganisms first. And we have studied biohydrogen production using exactly the same condition, starting with glucose in a batch reactor. And we have monitored over time the conversion of glucose and the amount of hydrogen recovered. Because in fact, there is a selectivity. I mean that you could convert all your glucose and have no hydrogen. I have only volatile fatty acids. So you have here the yield or the final volume, because in fact, hydrogen, when it is released, we recover it in a tank, and we can measure the volume of hydrogen using the flow rate of hydrogen. And this is the productivity. You could say it's the productivity over time of hydrogen. As you can see, we have a small increase in hydrogen yield in laminar condition. We have nearly a plateau here, but what is true is that we have a strong decrease under turbulent condition. It means that turbulent condition must be avoided. We could see laminar transition. The difference is not so big, but in this case, this decrease is very strong. So we have to limit the stress on our microorganisms. The question is that, of course, when you increase the size of a reactor, you can operate at constant power per volume, but it does not mean that if you work at constant power per volume, it does not maintain the same stress on microorganisms. And so what is important is also to be able to describe locally where are the zones where stress could be harmful for microorganisms. And in a small scale, we started, of course, the small scale, but the objective is to see that, for example, scale up with constant power per volume unit is a good approach or not a good approach for this. And so we need the 3D description. Of course, we are sure that close to impeller will have higher stress, but as you can see on this picture, in fact, due to the low agitation, we are zones in which agitation is very low. And this is not good, on the contrary, for mass transfer. So we have to find a trade-off and to see if mass transfer is good enough. And for that, we need precisely the 3D hydrodynamic field. I hope I have been clear and not too long.
Yeah, absolutely. 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 Now it's definitely clearer. Perfect. Then let me thank again our first speaker for the nice presentation. And for the sake of time, we have to move to the second presentation, which we will move then now to the quite far from Clermont-Ferrand. So the next speaker is Ali Mohammed, that is a PhD student at the University of Kwazulu, Natal in Durban, South Africa. And his presentation is about the application of centrifugal force for mass transfer enhancement in a falling film microreactor. So if Professor Vial needs to close the presentation, please stop sharing. So we have some problems now.
It should be stopped.
No? Not yet. We still see your your screen, unfortunately.
And now?
Okay, perfect. Then thank you very much. Then we can move to Ali. Then you can share your screen.
Hello?
Very good. Perfect. Then the stage is yours.
Yeah, you can hear me now, right?
Yes, all good. Perfect. Thank you.
Okay. My presentation is mass transfer enhancement in a falling film microreactor. That's the title, through the application of centrifugal force. In this study, a process intensification strategy focused on yielding higher rates of mass transfer in a falling film microreactor through the application of centrifugal force was investigated. This is
sorry, I have to interrupt you. Can you go to the presentation mode, maybe, that we can see it better?
Oh, okay. Can you see the slides now?
Yes, but just in your PowerPoint view.
Okay.
So if you can just go to the presentation mode, so maybe with F5.
Oh, okay, that's fine.
Otherwise, we can also see
the background,
like this.
actually. Okay, is it fine now?
I mean, we can see it. So if it's fine for you, we can go on like this.
Oh, okay, then that's fine.
Okay.
The benefit of using centrifugal acceleration for mass transfer enhancement have been listed here. It include the generation of mean acceleration that are thousands of times higher than the forces of gravity, formation of the thin liquid films which improve micro mixing capability, and higher rates of mass transfer between phases due to the reduced diffusive and conductive path lengths that are being created. These are one of the benefits, or rather the benefits that we want to explore by the application of centrifugal force in in the falling film microreactor. The theory here, the basics behind the theory is that the efficiency of a microreactor, or rather the efficiency of a falling film microreactor, largely depends on the generation of tiny liquid films that forms within the microchannel. And as a result of that, an increase in effective interfacial area for mass transfer is normally obtained. And this leads to higher rates of mass transfer between phases. Now, the question is, how do we generate the centrifugal field? Considering the geometry of the reactor. To be able to answer that question, we fabricated an in-house rotating jig, which applies the centrifugal force, which created the required centrifugal field for the falling film micro reactor. Now, to the far right is the a standard falling film microreactor suspended on the rotating jig. And this is the rotating jig. A photo of the rotating jig is shown here. And the rotating system comprised of basically two stainless steel components. One of it is a rotating, a solid cylindrical shaft, and a hollow cylindrical shaft that is housing the solid block. The apparatus is connected to a pulley and a driving belt that usually drives it. And inside the solid block, there are flow lines that have been drilled through the solid block, which are interconnected to the sleeve and then to the reactor. So fluids are being admitted through the solid block and then onto the reactor, in and out of it. So the experiment, for us to be able to basically, what we are trying to do here is to investigate the effect of centrifugal force on the liquid phase and gas phase mass transfer coefficient to see if there will be any enhancement as a result of the application of the centrifugal force. So for us to be able to determine the mass transfer coefficient, to carry out the measurement of the mass transfer coefficient for the liquid phase, we use the reactive carbon dioxide absorption for the liquid phase, as you can see in equation 1 here. And then for the gas phase mass transfer coefficient, we use the reactive absorption of sulfur 4 represented by these equations, as represented by equation 1 and 2. This is a flow diagram for the gas phase mass transfer coefficient. The liquid phase mass transfer coefficient is something similar to this, with a little modification on the gas supply, and then the absence of the gas phase, the gas analyzer, and then the absence of also the mixing chambers. Now to the results. Liquid side mass transfer analysis first. Based on the underlying principle behind the development of classic film model, the liquid film thickness is a priority in mass transfer analysis. Now equation 3, as it is seen here. Hello? Hello?
Yes, we can hear you.
Oh, okay. Equation 3, as it is seen here, is usually used in the determination of liquid film thicknesses in the falling film microreactor. For experiments that were purely conducted under gravitational influence, equation 3 was used to estimate the liquid film thickness. But for those that were conducted under the influence of centrifugal acceleration, in addition to the existing gravitational acceleration, the equation need to be modified. And for the fact that the forces, the two forces acted in perpendicular, in different directions to each other, that is the perpendicular, they acted in perpendicular positions to each other. We have to introduce, from equation 3, we have to substitute the acceleration due to gravity here with the resultant force, which is like an apparent gravitational force that is representing the two forces that have acted on the liquid film in different directions. And to be able to determine the resultant force, we use equation 5 to determine the resultant force here, which is representing the acceleration due to gravity and the centrifugal acceleration. This was, RF was, the resultant force was determined using an established theory of vector forces. Equation 6 shows the acceleration due to, equation 6 defines the centrifugal acceleration. And equation 7 was used to estimate comparison of the experiments. It's a graphical comparison of the experiments that have been conducted. The first one was conducted under a constant gas flow rate of 60 cm³ per second, while 60 cm³ per minute, while the second one was conducted under a constant gas flow rate of 220 cm³ per minute. Now, if you look at this, the first graph is liquid phase mass transfer coefficient versus the liquid flow rate with varying rotational speed of the reactor. Now, if you look at this first graph, this first line was the result that was obtained at 0 RPM, revolutions per minute, while the second one was at 55 and the third one was at 110. This red line represents what was obtained at 165 revolutions per minute. Now, if you look at this graph, the 3 lines here, a moderate increase in liquid phase mass transfer coefficient was experienced. But when the rotational speed of the reactor was increased to 165, the variation becomes a little bit more pronounced than the previous ones. Now, on the other hand, the second graph here also represents the experiment conducted at 220 cm³ per minute of the gas flow rate with the same conditions as the first one. But in this case, because of the increase in the effect of gas flow rate, we can see a significant rise from 0 RPM to 110 RPM, and then to this black line, which yielded the highest liquid phase mass transfer coefficient at 110. But in the case of this red line, which is 165, a drastic effect was experienced, which we presume was as a result of the increase in the gas flow rate with a combination of increase in the gas flow rate as well as the rotational speed of the reactor, which we can see it drastically impacted on the liquid phase mass transfer coefficient. This possible explanation for this could be related to the fact that a combination of these two parameters could have led to a reduction in the resident time within the reactor system. Fine. Now, we made a correlation attempt using a simple power law equation often utilized in the determination of gas phase mass transfer coefficient, which is the Sherwood correlation, as could be seen there in equation 8. But for the fact that we conducted our experiment under the action of centrifugal force, in addition to the existing gravitational force, we had to modify the equation to take into account the effect of the rotation, which was introduced here in equation 9. So this equation was modified to equation 9 to account for the impact of the rotational effect. Okay, for the various, before that, for us to be able to use this equation, we have to consider, because the equation itself was kind of established for a macroscopic level. So the conditions that were considered in modifying this equation 9 was the effect of centrifugal force on the fluid element, the geometry and size of the system that was used, and the hydrodynamic characteristic of the fluid elements in the system. This table shows the variation of the F parameter with the exponent X, Y, and Z at varying rotational speed of the reactor system that were obtained. We use a multivariable least square method for us to be able to arrive at these parameters. Now, using the modified equation with the experimental data, we observed that at 0 and 55 RPM, the predicted equation was well represented by the experimental data, while at 110 to 165, the representation was fair. These are the graphs. This is for 0 RPM, You can see the representation was fair within an error margin of 20 plus or minus 20%. This is for 55 RPM, and the third one is for 165 RPM. The gas phase mass transfer analysis, on the other hand, was also conducted, but in this case, we have to assume a system in which a plug flow of the gas phase occurs. And the reaction conditions were upheld to ensure that the gas phase is limiting reactant. And this enabled us to use equation 10, as seen here, for the determination of the gas phase mass transfer coefficients. The two graphs that are presented here, in this case, the absorption rates have been represented here as a function of the velocity and at various rotational speed of the reactor speed, at various rotational speed of the reactor unit. Now, this first graph here, it was an experiment that was conducted at a gas velocity of, at a liquid flow rate of 1.2 mils per minute with sodium concentration of 3.5. That's the inlet, and with the inlet concentration of SO2 at 1,730 ppm. The second one was diluted. The inlet concentration of SO2 was diluted to 918 ppm. And
I need to ask you to come to a conclusion because the time is running out.
Okay, that's fine. Yeah. But as you can see, the two graphs, the absorption rates seem to be higher when the inlet concentration of the gas is more diluted. We also made a correlation attempt similar to what we did in the gas phase, liquid phase mass transfer coefficients. This was also represented by equation 11. And then these are the exponents, the F parameters and the exponents for the modified correlation. This graph also represents the a generalized modified correlation that was used. So in conclusion, the rotational effect yielded a decrease in liquid film mass, and liquid film thicknesses that we observed. But most importantly, on a general note, Kg values, that is the gas phase mass transfer coefficient, were better predicted by the modified Sherwood correlation than the liquid side counterparts. Before I leave, I would like to play this video. It's an illustration of one of the experiments that were conducted. It will reveal how the reactor works. My sincere appreciation and gratitude goes to my supervisor, Professor David Lokhat, University of Kwazulu Natal, Reactor Technology Research Group, and to the National Research Foundation of South Africa for partly funding this program. Thank you so much for listening.
Thank you, Ali, for the presentation. If there are no urgent questions, we have unfortunately to move to the next speaker. I would like to invite you to address any questions to Ali during the coffee break or directly by email to him. So thank you again for the presentation, and we will move to the next presentation, which is from. Thank you. So the next presentation is from Politecnico di Milano. So we will have Claudio Ferroni. He is a PhD student, and he will introduce us to the experimental and numerical analysis of transport properties of cellular media to enable reactor scale simulation. Okay. So if Ali, can you stop sharing your screen? So we still see your screen. Perfect. Okay. Thank you. So Claudio, you can share your screen, please.
Okay. Can you hear me?
Yes, very well.
Okay, perfectly. I don't know. Can you see my presentation as well?
No, not yet.
Ah, sorry. Okay, I have to press the button. Okay.
Perfect.
Now you can see it.
Yes. So
okay.
you can start your presentation now.
Okay. So thank you to the chairman for the kind introduction. I am Claudio, and today I'm going to talk about the investigation of the transport properties of cellular media to enable reactor scale simulations. So this work is carried out aiming at the development of new structured substrates for catalytic applications. In particular, you might have seen in the lecture of Professor Freund on Monday how these geometries are considered in the process intensification. In my presentation, these geometries are considered in the field of environmental catalysis as new solutions are explored. In environmental catalysis, the chemical reactions that occur are often characterized by severe mass transfer limitations. So the conversions are mainly provided by the geometry of the supports. And also the pressure drop plays a relevant role, as a low pressure drop is required to avoid any engine penalty and to minimize the cost of processing of the pollutants. So as the requirement of reducing the emission nowadays is a topic of high significance, new solutions have been explored in this view to pursue this task. The honeycomb monolith is the state-of-the-art of these kind of applications in terms of structure catalyst. The honeycomb monolith provides very low pressure drop and high surface area for the deposition of the catalytic phase. On the other hand, it provides relatively low gas-solid transfer rates, so new solutions are considered to boost the gas-solid transfer rates. In particular, at the Politecnico di Milano, open cell foams have been considered in the past as potentially innovative solutions. They are characterized by a continuous irregular solid matrix with open cells. They are characterized by high porosity and high surface area. And in this view, they convey high gas-solid transfer rates. On the other hand, they provide a high pressure drop as well, which hinders their application, at least for environmental catalysis. Periodic open cellular structures are now considered. Periodic open cellular structures are now considered as potential innovative solutions. They are lattice structures which are made by the regular repetition of an elementary unit cell with well-defined geometry. Their manufacturing is provided by 3D printing, so it is possible to carry out an advanced design of the cells and the geometrical optimization of the carrier to tailor their morphology to the process needs. They are characterized by an open cell structure which provides intense radial mixing and convey a tortuous flow path to the reactant flow. In this view, they provide high gas-solid transfer rates. As their manufacturing is not established and they're not currently available on the market, the aim of this work is the assessment of the performances of the structure for mass transfer limited applications. So the investigation of the transport properties is carried out. The effect of the morphology is modeled to obtain engineering correlations to eventually enable a reactor design, and POCs are of course compared with the state-of-the-art technology. To carry out the investigation, computational fluid dynamics is employed. CFD simulations are considered as synthetic experiments which enable the fundamental investigation of the transfer phenomena as a function of the morphological properties. So it is possible to model the effect of single morphological parameters without any cross-influence. So it is possible also to obtain CFD-driven designs of such structure to maximize the performances in view of specific applications. As the modeling of an entire catalytic reactor results in an unfeasible computational burden, an adequate methodology was developed. In particular, as the scale of chemical reactors chemical reactors have way higher sizes with respect to POX unit cell sizes, and as in most of the applications, the fluid dynamics is deemed to be fully developed, periodic boundary conditions have been introduced to capture the effect of to capture the asymptotic transport properties in fully developed flow conditions. And the introduction of periodic boundary condition enabled the evaluation of the transport properties on small but still relevant domains, which are constituted by few unit cells, which represent a portion of the catalytic reactor. So it is possible to obtain asymptotic properties without any influence of any side effects, such as entrance effects or solid wall constraints. In this view, the asymptotic properties which are obtained are representative of most of the real conditions, where the size of the applications is way higher than the size of the unit cell. The first part of the presentation deals with the parametric investigation of the transfer properties and the formulation of engineering correlations. So here you can see the outcome of the gas-solid mass transfer analysis of POX. In particular, two geometries have been considered, which are the TKKD unit cell or Kelvin unit cell and the diamond unit cell. And the effect of the morphological parameters is hereby discussed. The strut size is chosen as a characteristic length. The strut is the minimum element which constitutes the POX frame, and the strut size is considered in analogy with the tube banks in heat transfer, and also as the struts is the minimum element which offers resistance to the fluid flow. So here you can see the Sherwood number, which is reported against the Reynolds number. And you can see the effect of the porosity and of the cell size. The Sherwood number increases with the Reynolds, of course, in contrast with the Onicon, which provides a constant Sherwood number. And as you can see, the Sherwood number decreases by increasing the porosity, whereas the effect of the cell size is properly included in the Sherwood dependency on the Reynolds number. The characterization of the diamond unit cell follows the same lines. So as you can see, the Sherwood number decreases with the porosity and is constant with respect to the cell size. As an outcome of this analysis, it was possible to formulate engineering correlations to eventually enable reactor design. The effect of the fluid dynamic condition on the Sherwood number is included in the Reynolds dependency, and an explicit dependency on the porosity was found. The pressure drop is additionally considered, as the modeling of the pressure drop is of high relevance in environmental catalysis. As you can see, the pressure drop is reported against the specific flow rate for the KKD unit cell and the diamond unit cell. And as you can see, the pressure drop increases with a linear quadratic dependency to the increasing flow rate, and also it decreases at increasing porosity and at increasing cell size. POX are compared with other technologies. In particular, the POX are compared with the honeycomb. POCs are considered at porosity equal to 0.9 to obtain low pressure drop, and with a strut diameter equal to 200 microns, which is compliant with the current 3D printing limitations. The structures are compared with an honeycomb having 900 CPSI and 2.5 mils, and C oxidation at 300 degrees C and 1 bar is considered as an example of a mass transfer limited reaction. So here you can see reported the volumetric mass transfer coefficient against the specific flow rate. As you can see, the honeycomb provides a constant KV, which is a function of the geometry only, whereas the KV of the cellular material increases with the increasing flow rate. In particular, the diamond unit cell provides the highest rates. An additional comparison was carried out with the foam, as they represent potential alternatives to honeycomb as well for several applications. A foam with same porosity and comparable surface area to POCs was considered, and as you can see, the performances of the foam is comparable to that provided by the TKKD unit cell. As a final outcome of this analysis, the mass transfer limited conversion is reported against the residence time for a catalytic application, and two working fluid velocities have been considered, being 5 meters per second and 25 meters per second. The four structures which were previously considered are hereby discussed. And as you can see, the honeycomb provides a constant conversion with the increase of the velocity at same residence time, as it provides a constant Sherwood number, whereas the conversion provided by cellular material increases with the increasing velocity. Moreover, the diamond unit cell provides the highest mass transfer limited conversion, whereas the TKKD unit cell and the foam provide comparable conversion at low velocity, and the Kelvin unit cell provides same conversion as the diamond at high velocity. The pressure drop is also discussed. As you can see, the honeycomb provides very low pressure drop, as the pressure drop is linearly dependent with the increasing flow rate. On the other hand, cellular material provide a linear quadratic dependency on the increasing flow rate, so they provide a higher pressure drop. In particular, the TKKD unit cell provides the highest pressure drop, whereas the diamond unit cell provides intermediate pressure drop. A foam was once again compared with same specific surface area and same porosity, and as you can see, the foam provides same pressure drop as the diamond unit cell POCs. So as an outcome of the analysis, the overall performances are discussed. In particular, as an outcome of the previous analysis, the diamond unit cell was proven to offer the highest gas-solid transfer rates, and the TKKD and the foam were shown to offer comparable performances, whereas in the study of the pressure drop, the Kelvin unit cell was proven to offer the highest pressure drop, whereas the Kelvin unit cell and the foam, whereas the diamond unit cell and the foam provide comparable pressure drop. In this view, the diamond unit cell is capable of providing the best trade-off between the increase of mass transfer and increase of pressure drop, at least among all cellular materials. So a final comparison with the honeycomb is carried out. In particular, two structures have been considered, one having 400 CPSI and one having 900 CPSI. And the overall performances of the diamond unit cells are compared here in these graphs. In these graphs, you can see the ratio between the volumetric mass transfer coefficient of the diamond and the honeycomb, which is reported by means of color, whereas the solid black lines provide the ratio between the pressure drop. As you can see, the diamond unit cell provides higher transfer rates at decreasing cell size and at increasing flow rate, which of course is in agreement with the behavior which was shown before. And as you can see, in the area provided by the dark green, the gas-solid transfer rates which are provided by the diamond unit cell are lower than that provided by the honeycomb monolith. On the other hand, at decreasing cell size and increasing flow rate, it progressively offers higher transfer rates. This is achieved, however, with the expense of higher pressure drop as well. For instance, considering a diamond unit cell having a cell size equal to 2 millimeters, transfer rates which are a volumetric mass transfer coefficient, which is 2 to 3 times higher than the honeycomb, is achieved, but higher pressure drop, which is 2 to 3 times higher than the honeycomb pressure drop, is achieved as well. The comparison with the honeycomb having 900 CPSI is along the same lines. On the other hand, you may note that to achieve greater performances, it is required to minimize the unit cell of the diamond and to outperform the honeycomb in real applications. So, in conclusion, as a final remark of this presentation, cellular materials were proven to offer indeed higher gas-solid transfer rates than the conventional honeycomb on the market. In particular, the diamond unit cell provides the highest gas-solid transfer rates. The Kelvin unit cell and the foam were proven to offer similar performances at same specific surface area. And on the other hand, higher pressure drop is achieved as well by employing cellular materials. The diamond unit cell and the foam offer comparable pressure drop, which is lower than the TKKD unit cell pressure drop. So the diamond unit cell was proven to offer the best overall performances, at least up to now, among all cellular materials. Thank you for your attention. I'm free for any questions.
Thank you, Claudio, for the clear presentation. Now it's time for questions. So please, from the audience, if you have any question, open your camera and your microphone, and you're free to ask to Claudio. I'm sure he is really happy to answer the questions. I have actually one question that is about the dependence of these results from the reaction, from the chemical reaction that you are considering. So is there, if I choose another reference reaction, would the results be different, or are they relatively independent?
This is a very interesting question. It depends on the reaction which is considered, also the working conditions such as temperature and pressure. The results which are reported here are always true for mass transfer limited reactions. So for reactions which are limited by external mass transfer limitations. So for instance, oxidation of hydrocarbons at high temperature, or DOC applications, these kind of applications. There are also benefits on applications which are partially limited by mass transfer limitations, such as SCR applications. For instance, my colleague, Dr. Mauro Bracconi, he discussed this aspect in his presentation. I think it was on Monday or Tuesday. Anyway, he talked about this aspect in the case of SCR reaction performances.
Perfect. Thank you. That's quite clear as an answer. So if there are no other questions, then for the sake of time, I will thank again Claudio for the nice presentation, and I will move to the next presentation that is also from Milan. So we will have now Federico Sasha Franchi, who is a PhD student at Politecnico di Milano. Yeah, so you are ready. Perfect. Hello. And the title of the presentation is Enabling the Evaluation of Mass Transfer Properties of 3D Printed Catalyst Substrates with Rich Hydrogen Oxidation. So Federico, you can just
I'm
share your
sharing the
screen. Perfect. So it's coming. Very good. And
Perfect.
then the stage is yours, please.
Thank you very much. So as Emanuele introduced, my study is about the evaluation of the mass transfer properties of 3D printed catalyst substrates with the rich hydrogen oxidation. This topic is linked directly to the work of my colleague Claudio Ferroni, but it focuses more on the, let's say, experimental aspect of this type of studies. As he already clarified, structured supports are widely applied in, for example, process intensification, or better still for this kind of studies in environmental catalysis, where mass transfer, external mass transfer limitations are a big problem and need, let's say, in-depth studies. Because if external mass transfer can be enhanced with better defined, or at least designed support, there can be advantages in terms of volumes of the catalytic reactors, or also in some cases better trade-offs between pressure drops, which are mainly driven by the dimensions of the catalytic reactor with respect to mass transfer. So one way to study external mass transfer in 3D printed complex structure is the use of CFD analysis. But if you want to prove, or at least have an experimental validation of these results, we need an experimental protocol which is reliable, if possible, economical, and because of the wide range and characteristics of this structure, fast and simple in the realization of the physical supports, and also under testing. Currently, the most common materials for the production of the boxes, for example, are metals or ceramics. Problem is that this kind of materials does not satisfy the key feature of fast realization and economicity, due to the need for or very expensive and complicated machinery, or outsourcing of their production. Also, currently, with the small dimensions of the elements comes a significant roughness, which is not ideal if we want to study the fundamental properties of these kind of supports. For this reason, the first, let's say, way to circumvent these limitations is to use a proven technology, which is the 3D printing of resin, which basically is conceptually as a better surface finish and accuracy of the printing, is cheaper, and provides in general faster printing times. Once we have prepared the support, the two issues are how to activate it for a test reaction, and how to actually test the sample. So from the production perspective, we have used a commonly available STL 3D printer, SLA 3D printer, but by using a high temperature engineering resin, we managed to produce quite accurate and precise samples. These samples can withstand up to 290 degrees mechanically. And then we started to investigate how to activate them. Previous studies on open cell foams relied and discovered that spin coating was the best technique to achieve a good catalytic coating, which was uniform in thickness and coverage, and also does not present pore clogging or adhesion problems. So we prepared a catalytic slurry made of an highly active oxidation catalyst, palladium on cerium oxide, to be more precise, in a mixture of water, glycerol, and PVA. This slurry was deposited by dipping on the 3D printed support, and the excess removed by spin coating. So we used the centrifugal force to push out the excess formulation. To consolidate the catalyst layer formed, a flash drying procedure was performed at 200 degrees to remove the liquid phase without deteriorating the resin. Then, once the support is coated and ready to be tested, can be loaded in a common tubular reactor, which consists in an external oven to control the temperature, two thermocouples to register the temperature at the inlet and at the outlet of the sample. And the gas mixture that is fed to this system is composed of oxygen, hydrogen, and nitrogen, with oxygen as the limiting reagent. This why? First of all, generally for this kind of studies, C oxidation was the preferred reaction. But due to the limitations of maximum operating temperature of the resin, this reaction cannot be operated in external mass transfer limitations. So it's not directly usable for the evaluation of external mass transfer properties. For this reason, hydrogen oxidation was chosen, which complied with the maximum operating temperature, reaching external mass transfer at temperature even as low as 200 degrees C, average temperatures. The problem is that hydrogen has a very high diffusivity, and from some calculations performed prior to the tests, we found that if hydrogen was used as the limiting reagent, significant differences between the expected conversion from assuming an ideal PFR behavior and the real system would have rendered the study completely unusable, and also the conversions would have been so high that experimental error would have been too important. For this reason, we decided to use oxygen as the limiting reagent in a vast excess of hydrogen to avoid any possible lean spot along the catalyst. Once we had decided that the hydrogen oxidation was the perfect, let's say, test reaction, we performed several runs, reactive runs over the prepared sample to verify that no degradation and change of the conversion, the mass transfer limited conversions were occurring, and so we also proved that the results were consistent throughout the testings. To validate this methodology, we also performed a direct comparison with the literature available correlations developed for open cell foams. For this reason, we calculated the Sherwood number for the foams, for 3 samples of foams, 3D printed and tested with this methodology. And we found that the results are in very good agreement with the predicted correlation. And to, let's say, further validate this methodology to other type of supports, we performed a cross-check between a sample created by with this methodology, so resin, a resin sample coated and tested with oxygen, let's say, reduction, so hydrogen oxidation in rich conditions, along with 3D exactly, let's say, a 3D printed sample made from the exact same STL file, but produced in aluminum, and tested with the, let's say, proven CO oxidation test reaction for the evaluation of external mass transfer properties. And moreover, the results from these two methodologies were validated against CFD results, also performed on the same STL file. And as you can see from the Sherwood values, the agreement between the various methodology is almost, let's say, perfect, and well within the experimental error for the 2 reactive tests. So just to sum up the key aspects of this methodology, the 3D printing with the SLA, with an SLA machine of supports from a resin, an engineering high temperature resin, enabled to produce in a short amount of time and in an economical way complex 3D structures with a very high degree of freedom. These structures can then be catalytically activated and tested in external mass transfer conditions to extrapolate their external mass transfer coefficient and to enable to develop correlation for their mass transfer behavior. These results can then be checked or cross-validated with CFD, and the let's say use of the experimental procedure along with CFD simulations is fundamental to let's say better screen through the vast amount of possible geometries that are enabled by 3D printing technologies. Thank you for your attention. So if you have any question, please ask.
So thank you, Federico. Thank you very much for the clear presentation. So as you mentioned, the room is open for questions. So please, if anybody from the audience has any particular questions or clarification for Federico, please feel free to ask. Then while the audience thinks about possible questions, I will just ask you, So do you have any other kind of measure to do for this reaction to avoid the external mass transfer limitations, or the reaction is anyway too fast?
I mean, I'm not sure I've understood the question. So you mean that if I'm sure that this reaction is actually in external mass transfer?
Yes, and in principle, if you can do anything else than changing the catalyst structure to avoid the problem of mass transfer limitations.
But actually, external mass transfer limitations are what this reaction was designed, let's say, for. So we choose let's say, a simple reaction, a one-step reaction, which is compatible with the temperature sustainable by the resin, which is sufficiently active to be in external mass transfer limitations conditions, so that we can exclude the effects of, let's say, chemical regime or internal mass transfer limitations. Regarding internal mass transfer limitations, we coated a very thin catalytic layer, which is around 5 to 7 microns. And also by analyzing the conversion at temperature lower than 200 degrees C, we, let's say, we proved that the regime was in fact limited by the external mass transfer. Mm-hmm. For example, well, actually, with this type of catalyst, we managed to say ignite the reaction at temperatures which are barely higher than ambient. So, okay. I mean, 35 degrees C on all the tested samples, conversions were already at 50%, something like that.
Okay.
And despite the activity, the high activity of the catalyst, the resin doesn't suffer any stability issues, any mm-hmm. oxidation or degradation. So the geometry remained throughout the test, mm-hmm. the one that was realized.
Perfect. Thank you, Federico. Any question coming from the audience? Don't be shy. So if not, I will thank you, Federico, for the nice presentation, and then I will move on to the next speaker. So now we go to Germany, where Julia Litvin is a PhD student at the University of Erlangen-Nuremberg, and she will introduce us to the heat transport characterization and geometric optimization of periodic open cellular structures. So I see that you already shared your screen, so we can directly start straightforward. So Julia, the stage is yours.
Okay, thank you for this kind introduction. You can hear me? Yes, I think.
Yes.
Okay. Yeah.
Yes,
okay,
perfectly.
Okay, so as you already told, Emanuele, I will talk about the heat transport characteristics of periodic open cellular structures. So we already heard a lot about the mass transport in periodic open cellular structures in the last 2 talks. And for the heat transport, POCs are also a very good alternative to randomly packed beds, since in randomly packed beds, besides the high pressure drop, we also have a low radial heat transport. So in this regard, structured catalyst carriers, such as also open cellular foams, or in this case also periodic open cellular structures, so show great potential as an alternative to randomly packed beds. These POCs are, as you might have heard, built from a unit cell. This is repeated in all three spatial directions and thus form a three-dimensional network of struts. So, besides the low pressure drop and the high radial mass transport, also the high radial heat transport is a great advantage of those POCs. The well-defined morphology also enables systematic investigations, which I will show today for the heat transport. And with the high design flexibility, also geometric optimization of the geometry is possible. However, either to design or to optimize the geometry, models to describe the transport characteristics are necessary. These transport characteristics are, for example, the pressure drop in multiphase operations, also the liquid holdup, and also the heat conduction, and what I'm talking about today is the overall heat transfer. In this regard, we made a special focus on the influences of the geometric parameters of the POCs on the resulting heat transfer and also on the model parameters, which is possible due to the possibility of the systematic investigation of those POCs due to the regular geometry of those structures. The geometry of the whole structure is defined by the unit cell parameters, which are shown here for this diamond unit cell. Its important measures are the strut diameter, the cell length, as well as the window diameter, which is the diameter which is accessible for the fluid, and also the porosity of the whole structure is very important. We investigated in total 13 structures, which were all based on the diamond unit cell. Here we used two different materials with different solid thermal conductivities. Furthermore, the structures had different porosities, strut diameters, and also cell lengths. We investigated those structures in a double pipe heat exchanger, which is shown here. The structures were inserted here while heated from outside via a thermostat, while air was flowing through. The structures were additionally wrapped in aluminum foil in order to increase the wall contact. With 3 multi-point thermocouples, the temperature profiles could be measured at 3 different radial positions, as shown here. And by moving these thermocouples in axial direction, an axial and radial temperature profile could be obtained. These temperature profiles were then used to model the heat transport in the structures. Therefore, we used the so-called alpha W model for the modeling of this heat transfer. In this model, we have two defining heat transfer coefficients, namely the wall heat transfer coefficient and the effective thermal conductivity. By fitting the measured temperature profiles with this model, a pair of alpha W and lambda R could be determined for each operating point. These values were then used for the development of the correlations for the heat transfer coefficients. Since these two correlations for alpha W and lambda R can be expressed independently, I'm going to start with the presentation of the correlation for lambda R. What you can see here are the determined values of lambda R in dependence of the superficial mass velocity for one example structure. As you can see, there's a linear dependency of the thermal conductivity and the velocity. Lambda R can be expressed via a linear fit, and where lambda 0 is the stagnant thermal conductivity and the slope n describes the flow-dependent part of the contribution. This means for each structure, we get a value for lambda 0 and the slope n. For the further development of the correlation, we checked lambda 0 and the slope n for the influences of geometric properties of the structures. For lambda 0, we found a dependency on the porosity. This is shown here, and where lambda 0 is shown in dependence of the porosity of the structures. Each point here refers to one examined structure. As you can see here, with higher porosity, the stagnant thermal conductivity gets lower. This is quite straightforward, since with higher porosity, there's less solid material available, which can attribute to the heat conduction. For the slope M, we found a dependency on the strut diameter, which is shown here. Again, each point refers to one examined structure. And there's a clear linear dependency of this slope M towards the strut diameter, which is the reason why we chose the strut diameter as a characteristic length for the description of the flow-dependent contribution. In order to model lambda 0 in more detail, we used an established approach, which was already used for foams and epoxy with other unit cells. Here, lambda 0 can be expressed by a parallel connection of the parallel and serial connection of the thermal resistances of the solid and fluid phase. Here, as you can see, also the porosity is here also taken into account. With this parameter B, the shares of the two different connections is then described. Also for this parameter B, we checked for influences of the geometric parameters of the structures. Therefore, we determined a value of B for each structure and found that the parameter B depends on the window diameter, as you can see here. Again, each point here refers to one investigated structure. In order to implement this finding in our reciting model, we used a linear fit for the parameter B with two fitting parameters B1 and B2. The reciting model looks then like this. We have three fitting parameters B1, B2, and KR. And as you can see in this parity plot, we get a very good fit for our experimental data with almost every point within the plus minus 20% region and a mean average percentage error of 6.6%, which is really an excellent value. So now I will go on and show you the correlation for the determination of the wall heat transfer coefficient. Here we also used an established Nusselt-Reynolds approach, which is shown here. And first here we wanted also to check for a suitable choice for the characteristic length. And here we found that the wall heat transfer coefficient is depending on the cell length. And this also is the case for different flow velocities, as you can see here. Here alpha W is shown against the AC for three different flow velocities. This is the reason why we chose this cell length as a characteristic length for the description of the Nusselt number at the wall. Again, here we checked the model parameters for influences of the geometric parameters, and here we found that the parameter A, which can also be referred as the static Nusselt number, is depending on the strut diameter, as you can see here. Also here we determined this parameter A for each structure and checked for influences of the geometry. Also here, we implemented this parameter as a linear fit with the two fitting parameters A1 and A2. The reciting model is shown here again. We have four fitting parameters A1 and A2 and B and C. The parameters B and C were fitted as constant parameters since we didn't find dependency of the geometric parameters. The parity plot shows again a very great fit for our experimental data with a few values over 20%, but most of the values are within this plus minus 20% region and a mean average percentage error of under 10%, which is especially for the determination of the wall heat transfer coefficient an excellent value. So now I showed you the correlation with which we can determine the heat transport characteristics of diamond rocks. Now I show a quick comparison to randomly packed beds. And some of you might have heard the keynote lecture of Professor Freund, of my boss. And there he showed a similar nomogram for POX with cubic unit cells. And again, I explained it quite quickly. We have here the relation between the overall heat transfer coefficient over POX and a randomly packed bed with the same specific surface area. And this is shown in dependence of the solid thermal conductivity of the structure and the superficial mass velocity. The different solid thermal conductivities correspond to different solid materials. This black line indicates where the overall heat transfer in the box is the same as in the randomly packed bed. This means in this region on the left, the POCs have a higher heat transfer coefficient than the packed bed, and on the right, the packed beds outperforms the POCs. So what in comparison to the nomogram shown by Professor Thorn for cubic unit sets, we can qualitatively say that there's the same effect, that the POCs are better, especially at low velocities. However, the region where the POCs are better varies and is depending on the unit cell geometry. This means that for the diamond POCs, we have a greater region where the POCs has a higher heat transfer than the randomly packed bed. Another great advantage of the POCs is the pressure drop. And in combination with the heat transfer, it's always a trade-off between the pressure drop and the heat transfer. And I wanted to show it in this graph the potential in comparison to randomly packed bed regarding the combination of heat transfer and pressure drop. Here is shown the overall heat transfer coefficient versus the pressure drop for a range of geometric properties. For one in green for packed beds, and in blue and red for diamond POCs. In blue for a lower solid thermal conductivity, and in red with a higher solid thermal conductivity. The black dashed lines indicate the same specific surface area as shown in this example before. And what we can see here is that when there's only a certain pressure drop allowed in your reactor, the overall heat transfer in the packed bed is significantly lower than in the comparable POCs, even compared to the POCs with the lower solid thermal conductivity. On the other hand, when we need a specific heat transfer in our reactor, we get a much lower pressure drop in the POCs than in the randomly packed bed, which you can see here. So it's 10 times, the pressure drop in the POCs is 10 times lower in this case. However, it's always an optimization problem, also for the POCs in regard to residence time and catalyst inventory. So POCs are perhaps not always the one solution, but they may be in other applications, they may be the best solution. So it's always an optimization problem. So with this, I want to conclude and make just a quick summary. We did some heat transfer measurements and checked those measurements for geometric influences of the structures. And these findings were also used for the model development for the heat transfer. And the validation showed a very good fit for our experimental data. And also in comparison to randomly packed beds, we see the great potential of the use of POCs in regard to heat transfer and also the pressure drop. With this, I want to thank you for your attention, and I'm happy to answer your questions now.
Very good. Thank you, Julia, also for the perfect timing. So as you already mentioned, the floor is open for questions or clarification or any kind of... so, Giampiero Groppi, please.
Thank you. Julia.
We are seeing your what you are doing, Giampiero. Sorry, it's a bit ugly. Your camera is, I think, turned the other way around.
Ah, sorry, no, it's the other camera.
Oh, okay, perfect.
I was making my lecture just before of this.
Okay, now you are upside down, but
sorry for that.
Coming
to the question. Now it's fine.
Perfect, thank you.
Okay, sorry. Julia, I wonder about, you showed that the static conductivity can be measured by using the classical in parallel in series approach.
Yes.
Weight combination of the two contributions, but introducing the D parameter, introducing a weak but not negligible dependence on D window.
Of what?
On DW, which I guess is not the strat, is the window of the structure. And I wonder if you have some physical insights about this second order dependence, let me say, since it's not that strong according to the showing.
Yeah, okay, so I wanted to look for influences of this parameter B, since as you can see, it's not quite constant over along all the investigated structures. And the most significant dependency was of the window diameter. And I explained it like this because it's all, the influences are all combined, since in the window diameter you have also the influence of the strut diameter and also the cell length. So, and also the specific surface area. And I think the specific surface area is here the most important value, since with higher window diameter, you get a lower specific surface area, and therefore less area which can attribute to the heat transfer. And this with higher B, you get a higher share of the series connection, which is the lower limit of the.
I got it. So it looks something related to gas solid is transfer actually.
Yeah.
I wonder if an heterogeneous model can better decouple the effects. You use a pseudo-homogeneous model.
Yes.
Right?
Yeah, okay. Yeah, perhaps heterogeneous models are mostly more detailed than pseudo-homogeneous models. However, with regard to the application, we wanted to use a pseudo-homogeneous model since it's easier to applicable also for the optimization of the heat transfer in the structures.
Thank you. And sorry for the camera.
It's fine.
No problem. Thank you. Thank you very much for the question. And
thank you too for the question.
Are there any other questions from the audience coming? If not, we will then move to the next speaker. Thank you again, Julia, for the presentation. And then with the next speaker, we go back again to the University of Clermont-Ferrand with Zainab Trad, who is now introducing us to the influence of the gas phase on hydrodynamics and gas transfer in a stir tank under anaerobic dark fermentation conditions. So you are still muted, Zainab. You should just unmute yourself. So still muted?
So,
okay. Now
good
it
morning,
works.
everybody.
Perfect.
Okay. You see the share of my screen or not?
Not yet.
Okay. And now?
Now we lost your camera also.
Also?
Yes, we are not seeing you anymore.
Okay. And now you see. For the screen is okay because I just press écran partagé. For me is okay, but
no, unfortunately we don't see. Now we see your camera again.
Yeah, but for my screen,
yeah, no, unfortunately not yet. That is strange.
On the green.
Exactly. Yes, on the bottom.
Yes.
Yeah, on the bottom.
And then you should have the choice of what to share.
But I cannot. Okay. Do you see?
Okay.
anything?
Yes. So something is coming.
Okay. And now is okay.
Okay. Yes, we see your PowerPoint.
Maybe I put it in full screen. Is
Exactly.
better?
Yes, that would be better.
Full screen. Is okay.
We are still in presentation mode. Okay, now it came. Perfect.
Okay.
So we look forward to your presentation.
Okay. Good morning, everybody, and thank you for this introduction. My name is.
Just sorry,
yeah,
we don't see your camera anymore now.
I don't know, and now.
Okay, now you're coming back, I think. We see a black screen, unfortunately. Okay, now. Okay, there is a bit of fog, but okay, perfect.
Okay.
So we see you. Perfect.
Is,
sorry for the problems.
Sorry for this problem. Good morning, everybody, and thank you for this. Thank you for this introduction. My name is Zainab, and I'm a researcher at Pascal Institute from University of Clermont-Ferrand. And today I will talk to you about the influence of the gas and phase on hydrodynamics and gas transfer in a stirred tank reactor under anaerobic dark fermentation conditions. Now another problem. I cannot pass to the second slide. It's okay. The outline of here is the outline of my presentation, and I will introduce for you and I will give you for you the introduction and the scope of this study, and after that I will give you the main objectives and I will pass to the methodology and some main results, and I will conclude and I will give you some perspectives. As Professor Vial today this morning said, my work is a part of the challenge of the energy challenges, and we search in our laboratory to improve the dark fermentation process. And to improve this process, we sorry, because I have my sorry.
Zainab, we still see your screen, so.
We don't hear the microphone. There is no
yes,
voice.
it's off the microphone. That's the point.
Zainab, could you please switch on the microphone?
We cannot hear you without the microphone.
Yes, now we see and hear. Yeah.
We hear, we see you, yes,
okay.
And we see your slides.
Okay, where is now my presentation is here. Okay, it's that. Okay, everything is okay now. Okay.
Yeah, only the slides are in your view, not in the presentation mode.
Yeah, I let it like that is better for me and for you. Okay, as I said, like we work in the challenges for second generation biofuels and to investigate more production of second generation biofuels. We use for that anaerobic digestion process using a steric tank reactor, and as we can see, we have here we can put for example organic wastes or anaerobic bacteria, and for the output we have for example the monoxide of carbon or bio-H2 biohydrogen, and for the liquid phase we have volatile fatty acids. The objective of this study is the mass transfer gas liquid in the liquid phase under the mixing conditions of the dark fermentation process. We have used some fluids like Newtonian and non-Newtonian. With Reynolds is of the range of from 2 to 11,000. We have also do a comparison with the flow structures obtained by CFD and some optical experiments. The final goal of this study is to optimize, as I said, the process, and we have for that we must have an homogeneous reaction medium, but we must be careful about the low shear impact on the bacteria, and also we must have a low power consumption at the end of the process with an optimal gas transfer. Some material and methods we have used it in these studies. We have used a 2-liter bioreactor or serial tank reactor, and as we can see here, we have two Rushton turbine, and we have used a transparent model floats with the same rheological property. For the optical experimental, we have used PIV 2D 2C using PCU camera PCU Max speed camera and a continuous laser, and we have compared these results with CFD computational flows dynamics using a Phoenix software. Here I have normally video for experimental setup using a planar laser induced fluorescence to compare with the CFD. We have used a tracer fluorescence with we have injected it in the tank, and as we can see, we have used a laser and a camera, and I don't know if you see the video. Normally is here the video.
Yes,
and,
it's working.
Okay. And at the same context, we have also used another experimental with a chemical discoloration using a chemical purple plus NaOH, and using the same setup. And as we can see here, we introduce the tracer, and we collect the images, and after that we do some treatment using software and using MATLAB code. Now we can pass to experimental and numerical results here. Hello? Yeah.
So we unfortunately lost the connection with Zainab. So let's see if we can recover her soon. More important than expected.
Yes, sure. Well,
so we will just probably wait until noon if she reappears. And then eventually we will just be free to go back to our coffee break to prepare for the next session.
Okay, maybe we'll try to contact her. Maybe we will have, if there will be possibility, maybe to shift to some other time. So
yes,
at the moment I cannot say what happened. I'm sorry for this.
Yes, no problem, Andrei. Thank you for taking care. And what I can just suggest that we wait until the nominal end of the session.
Yes, five minutes, right?
Exactly.
Let's wait. Okay. Okay.
So as it is noon, and unfortunately we cannot recover our last speaker,
yes,
I would just suggest that we close this session so that we can restart on time in 20 minutes with the next sessions.
Okay,
so
thank you, Manuel. Thank you very much for your work.
Thank you, Andrei. So I also thank all the speakers of this session, and I hope you enjoyed this session. And I look forward with all of you to the next session this afternoon. So thank you very much.
Thank you, bye.
Hello everybody. Welcome to the 7th and last session dedicated to the advances in chemical reactor fundamentals. My name is Carlo Giorgio Visconti, and I am an associate professor of chemical engineering at Politecnico di Milano in Italy. Today I have the privilege and honor to chair this very interesting session, which will include contribution on chemical kinetics, transport phenomena, and reactor modeling coming from 6 different countries and 7 different research groups. I just remembered to all the speakers that presentations of about 15 minutes are highly appreciated, so to leave some time for questions. And we can now move to the first speaker, who is the PhD student Jan Nemec from the University of Chemistry and Technology in Prague. And Jan is going to talk us about the modeling of internal transport limitations in catalytic particulate filters. So please, Jan, floor is yours.
Good morning, and thank you for your introduction. Can you all hear me, please?
Yes.
And do you see my presentation?
Yes, we see it as well.
Very, very good. Thank you. So once again, thank you and good morning. A lot has been already told about catalytic converters, and probably everybody here knows what does a monolithic reactor looks like. However, there is one more similar device in automotive industry, in vehicles, which is a particulate filter. This device is supposed to capture particulate matter, which is mostly soot or some fly ash. And a particulate filter is also a monolithic cylinder, as we can see here. However, each channel is plugged at one end, so the gas can flow in. However, it cannot flow out using the same channel, and it has to permeate through the wall. It has to filter, and then it can go out via the other channel. This particulate filter, which are mostly known from the diesel engined vehicles, has no catalyst inside. However, the current issue is if we can put some catalyst into the filter and combine two devices into the single catalyzed particulate filter. It would mean space, weight, and cost savings. However, the problem could be that there are some key parameters that should be reached, and these are high catalytic activity, high filtration efficiency, but also low pressure drop, which is a bit opposing. These parameters are defined or affected by some properties of the filter, and it can be a little bit tricky to design it properly. So we use math models of filters to predict some dependencies between those properties and those parameters. In this work, we focused on the prediction of conversion of the reactants in the catalytic particulate filter, and we wanted to implement the diffusion limitation into the filter wall in 1D plus 1D model of the filter. So please let me introduce the 1D plus 1D model of particulate filter very briefly. It's a classical engineering model which solves mass, enthalpy, and momentum balances. And it assumes a 1D plug flow along the channels and 1D perpendicular flow across the wall. If we take a closer look into the wall, we can say that the gas flows mainly using the free pores in the wall substrate from the inlet to the outlet channel. However, the catalytic centers are inside the coating and they are reachable via diffusion. So there is some transport limitation, even though the gas is forced to permeate through the catalytic wall. We know two mechanisms of mass transfer here. First, we are talking about a diffusion between the, let's say, bulk gas inside the pore and the catalytic coating surface. And the second is the diffusion inside the coating from the surface to the active sites. In this work, we use a model reaction, which is catalytic oxidation of carbon monoxide, which can be described by the Langmuir-Hinchelwood kinetic law without the inhibition of oxygen, and how to describe these limitations. Well, the first possible approach is to suppose that all the resistance, or the most of the resistance, is situated inside the pore. So we focus on it, and we know that there will be some concentration gradient between the catalyst and the bulk gas. So we add into the model a new concentration, a surface concentration of the reactant, which is unknown for us. And we say that the reaction is a function of this new surface concentration. This heterogeneous model, which uses two phases, gas and the surface, has new balance equation, which basically just say that the amount of a component that goes to the surface is equal to the amount of the component that is that disappears by a reaction. And it gives us the value of surface concentration. So the point is that the reaction is different now thanks to using the surface concentration, which is dependent on some diffusion properties. So this is how the diffusion will affect our effective reaction rate. The other possible approach is to suppose that the resistance is situated inside the coating. So we suppose that the concentration on the surface is the same as the on the surface is the same as in bulk gas. However, the concentration at the active site is lower. So we again need to modify the reaction rate somehow. And to do so, we use an effectiveness factor model. First of all, we calculate a Thiele modulus, which is a dimensionless number, which compares the rate of reaction to the rate of diffusion. And once we know the rate, we can calculate the effectiveness factor, which is a multiplier which modify the theoretical reaction rate to get the corrected or the observed one. So again, we have some factor which is dependent on diffusion properties, and it affects the reaction rate. What are the relations between the diffusivity, diffusion length here, and the effectiveness factor? It's a little bit more complicated. As for the first order kinetics, it would be absolutely beautiful because we can analytically solve the differential equations and get that for this Thiele modulus, the effectiveness factor has to be calculated this way. This is analytical solution. You probably have seen it somewhere, or at least something similar for a pellet. For the second order kinetics, usually we use something called generalized Thiele modulus, which is very similar, and the effectiveness factor is usually calculated the same way. The problems come with Langmuir-Hinshelwood kinetics because there's no analytic solution to these nonlinear kinetics. And we use some relations that were earlier found that are approximate. It is set of some complicated relations which work under certain circumstances. So it's a bit more complicated approach, but we adapted it somehow. The Thiele modulus looks the same as in the first order reaction. The important point of the Langmuir-Hinshelwood approach to this is there is possible to have an effectiveness factor higher than 1. It's because of the inhibition, which can be relevant under some concentrations of CO, and the effective order on the reaction is negative. So then more CO could mean lower reaction rate, so effectiveness factor is higher than 1. For our simulations, we also used detailed 3D model, which uses CFD techniques. It uses a reconstructed porous medium of some real filters, and we used a conversion profile, which was predicted by the detailed 3D model. And we tried to reach the same conversion profile using 1D plus 1D model by fitting the parameter diffusion length. So that's what we wanted to do. We did it using different filter sections with different coating distributions. And we also checked different gas compositions to see if the model is somehow robust. Let's quickly get over some of the results. First of all, we can see the plots for low CO concentration, which means we can assume there's no inhibition. and there's excess of oxygen, which means the concentration of oxygen is almost constant. In other words, this is a pseudo first order reaction. The red line here is the profile predicted by the 3D model. So it's the line that we wanted to reach. It's our goal line. And you can see that in this situation, all the approaches give very similar results. There's just a small difference for the second order approach of homogeneous model, which is given by the 3/2 constant in the Thiele modulus definition there. If we lower the concentration of oxygen to the stoichiometric one, we can see the results are a bit more different. We can see a very good result of the heterogeneous model. And out of the homogeneous models, the best results are given by the second order kinetics. Well, low CO concentration, still negligible inhibition. Stoichiometric O2, it is a pseudo second order reaction. So it's not a big surprise. And we can take a look at high CO concentration, where we need to consider inhibition in excess of oxygen. And again, we can see heterogeneous model gives very good results. And also the Langmuir-Hinchelwood approach to the effectiveness factor gives pretty good results as well, which is good for the inhibition reaction. However, just notice that we have to use different approaches of homogeneous model for different compositions. Here, where we had stoichiometric O2 but low CO concentration, the LH line, the dark blue line, did not work so well as the second order one. Finally, for high CO concentration and stoichiometric oxygen, again, all the lines are pretty similar. However, the second order line, light blue, is still best, which is actually maybe a little bit surprising because there should be some inhibition influence, but the second order deals well with it. And again, heterogeneous model works well. So maybe we could say the heterogeneous model is just fine. It gives consistent good results. The problem with it is with light-off curve, because you can see the heterogeneous model at higher flow rates gives us low conversion at high temperatures. There is some CO slip, which is not realistic. We are working on some relevant experimental data we could directly compare to these. However, we know this is not a realistic result. Actually, for very high flow rates, like 200,000 per hour, it's space velocity, there is some CO slip. However, it's very, very small. So the best approach in this view should be combining the classical heterogeneous model with effectiveness factor, because then we can set the model the way the CO slip is seeable, but very little, and we can even set the influence, the degree of both contributions to the transport limitation. So to conclude my presentation, I would like to summarize that all three approaches has some pros and some cons. A homogeneous model, which uses effectiveness factor, is very simple to calculate. The calculation is very fast. However, we have to use different settings, different set of relations between TLA modules and the effectiveness factor to get good results. And if we use only the Langmuir-Hinchelwood relations, the results are not so consistent, even though it should be the best option. Heterogeneous model, which considers mass transport between the gas and surface, is much slower. However, it gives consistently good results as for the conversion profiles. But we saw it overestimates the transport limitation at high flow rates. So we can combine these two together. We can use a heterogeneous model, including effectiveness factor. The problem is it's still quite slow. We have two fitted parameters now, which can be pretty problematic. However, we can estimate the diffusion length somehow if we have some information about the filter. And this approach is realistic, and it's valid in under the most conditions that we studied. I thank you for your kind attention.
Thank you, Jan, for your very nice and fundamental talk. We now have room for questions. So if anybody from the audience has some question, please open your mic and turn on your camera and feel free to ask. Don't be shy. I'm sure that Jan will love to answer some questions.
Sure.
Maybe I can ask one. You mainly focused on, during your talk, on mass transport limitation, right? Mm-hmm. What about the co-presence of heat transport limitations? Is this changing somehow your results, or do you expect the results be still valid even in this condition?
Well, in our model, we suppose there's no radial temperature gradient.
Right.
So at every action node, the temperature is the same across whole wall. So in this way, the heat transfer should not affect this very much. And as for the conversion profile, these were simulated isothermically.
Okay, but in case you have to manage a condition where you do expect temperature gradients, do you expect that your results in terms of the best model will still apply?
Well, since the channels are really small and the walls are even thinner, there's the assumption of no radial temperature gradient across the wall is reasonable. It really works. We can assume there is some temperature gradient as for the whole monolith filter. There are some heat loss, etc. However, this should not affect very much the detailed or the microscopic behavior of the gas inside the monolith. We use then only some correction factor for the part of the filter that should be affected by heat loss.
Okay.
To the surroundings.
Thank you, Jan, for your excellent talk again.
You're welcome.
And please welcome our next speaker, with the PhD student Alejandro Romero Limones from the Metropolitan Autonomous University in Mexico. And this is a joint contribution from this group and the research group in Ghent University in Belgium. And Alejandro is going to present us a paper titled Heat Transfer Analysis on Alpha-luminant titania as the support material for the oxidative dehydrogenation of ethane in an industrial wall-cooled packed bed reactor. So, Alejandro, the floor is yours.
Okay, perfect. Can you see my screen?
Yes, and we hear you well.
Okay, perfect. Okay, well, first of all, good morning. everyone. Next, I will present the progress made on the work entitled Heat Transfer Analysis on titanium support material for the ODH of ethane in an industrial scale well cool packet bed reactor. This work is still in progress as a collaboration between the Metropolitan Autonomous University in Mexico City and the LCT group from the Jugend in Belgium. So, yeah. So, multitubular wall-cooled packet bed reactors with low two-to-particle diameter ratio are industrially used to carry out high exothermic reactions as the selectivity of oxidation of hydrocarbons. Commonly, the assumption that one single tube performance is the same as the other tubes is considered, and based on that, these kind of reactors are modeled. So this type of reactors have high void fraction because their geometrical configuration, which improves the dissipation through the wall of the heat generated by the exothermicity of underside total oxidations. The effect of the void fraction, largely in fluid dynamics and also in heat transfer, has been studied for this kind of reactors, aiming at generalizing pseudo-continuous model to describe the reactor performance. Nevertheless, yeah, to this day, and to the best of our knowledge, there is no generalizing model able to describe the performance of this kind of system for high exothermic reactions. For the figure of the right, you can see that lines cannot describe properly the experimental data due to the lack of reliability in the a priori knowledge of the transfer phenomena and kinetics. That's something still in progress. Furthermore, the high temperature sensitivity to small changes in the operating conditions leads to significant variations in the reactant temperature, as could be here the hotspots. So, regarding transfer phenomena characterization, on fluid dynamics, the Navier-Stokes-Forchheimer equation is one of the most questions used to describe the velocity profiles within this kind of systems. Nevertheless, there are some issues and well, to describe the velocity profiles in the systems, as could be the use of the fluid viscosity instead of the effective viscosity, which overpredicts the velocity profiles within the system, as well as the non-mass conservation through all the packet bed length. On the other hand, the heat transfer mechanisms have been addressed by a 2D pseudo-homogeneous model, considering the effect of the fluid flow and hydrodynamics, and also the effect of the mean parameters, as could be the rel effective conductivity and the wall heat transfer coefficient. So the first one captures the mechanisms within the bed in the horizontal bed, and the second one captures heat transfer resistances in the zone near to the wall. Sorry. Here you can see an example from literature in which the high temperature gradient exists in the wall zone, and an hypothesis that we have is that mean parameters cannot characterize properly these heat transfer resistances. So the use of a pseudo-local heat transfer parameter, as could be the rel effective conductivity, can improve the characterization of the heat transfer in these kind of systems. So if this pseudo-local parameter is determined, its effect can be seen in a reactor modeling, comparing with the conventional approaches which have mean parameters. Thus, in this work, the oxidative determination of ethane is taken as the case of a study to evaluate the aforementioned pseudo-local heat transfer approaches in this reaction, and this reaction was taken because it's a promising reaction that has not been implemented at industrial scale due to the lack of technology and understanding of the transfer phenomena as well as kinetics. So with the above, the objectives of our work is to evaluate the impact of the fluid dynamics and also the heat transfer mechanisms on a packet bed reactor for this case of a study. And also is wanted to assess the pseudo-local rel effective conductivity in the heat transfer mechanisms. So to reach this, this system, well, as a packet bed reactor with low two-to-particle diameter radio, was decoupled into different zones, assessing the different heat transfer mechanisms in each zone. And also it's wanted to set the most reliable reactor model, considering the proper characterization of the transfer phenomena. So the methodology is next. First, we start with the experimental design for fluid dynamics and also for heat transfer. For fluid dynamics, the pressure drop experiments are necessary to characterize alpha and beta parameters from air communication, which will be helpful to determine other parameters and then estimate the effective viscosity to describe the velocity profiles within the bed. In the case of heat transfer, we follow a 2D pseudo-homogeneous model, and we estimate the parameters axial effective conductivity, real effective conductivity, and also the wall heat transfer coefficient, matching the temperature profiles with experimental data at bench scales that we performed in our laboratory. Finally, if we have a reliable simulation that match with our experimental data, we can integrate fluid dynamics, heat transfer, and kinetics with the reactor model. Here, I didn't mention it, but we follow a kinetic model from our research group for the ODH. So for fluid dynamics, this is the experimental system that we follow, where we perform the experiments, the pressure drop experiments. It's a bench scale containing spheres of titania. This bench scale has a tube-to-particle diameter ratio approximately of 3. So once the pressure drop is obtained, I mean, air is fed in the bottom of the packet bed, and the pressure is measured in the inlet and outlet of the system. So once the pressure is known, we estimate the parameters alpha and beta from Ergon equation, and then we calculated parameters K and Kc. And then with that information, the only parameter remaining to be estimated is the effective viscosity. So to estimate this parameter, we ensure that the mass conservation criteria is met. So for the heat transfer, there is 2 kinds of experiments. First, the axial temperature varying experiments, which consist in the same packet bed reactor heated by an infrared lamp from the top of the bed, and fiberglass insulated the tube with the aim to avoid radial heat transfer in the system. So with these experiments, we look to characterize the axial effective conductivity. Now, for the radial heat transfer experiments, we use the same system, but now an electric resistance is used to heat the system. And in this case, we wanted to estimate the heat transfer parameters in the radial direction. But which kind of radial heat transfer parameters? So in the figure on the right, illustrate in different zones a qualitative temperature profile for this kind of systems, considering any source, any heat source in the bulk zone, here the red zone, that is used on any industrial packet bed reactor for high exothermic reaction. So at first axial positions of this system, there is a decrement in the temperature bulk zone until the external surface of the tube, which is very difficult to measure industrially. Then this a second temperature gradient between the internal surface of the tube and a distance from the tube until the core zone. And finally, the core zone, which is shadowed in blue, it's captured by effective conductivity. So with this, the parameters, the real effective conductivity and the wall heat transfer coefficient have been estimated with this cross-correlation issue, and it captures the heat transfer mechanisms within the system, but also in the external surface of the system. However, considering these two both mean parameters has not been enough to properly describe the temperature gradients from experimental data. So in this case, we propose the use of a pseudo-local heat transfer parameter aiming for the better characterization of this. So we take an idea from the literature to obtain this pseudo-local radioeffective conductivity. And also we eliminate the cross-correlation between the parameters of the radioeffective conductivity and the heat wall transfer coefficient. So once we obtain this pseudo-local radioeffective conductivity, we use these three boundary conditions. The boundary condition B to just estimate the radioeffective conductivity, so the local one will also mean, and knowing the temperature in the internal surface of the tube. Then using the mu parameter estimated here, we can use that information as an initial guess to re-estimate the same parameter and obtain also the wall heat transfer coefficient, minimizing the cross correlation. But also, if we obtain the radioeffective conductivity so the local, we can obtain an external wall heat transfer coefficient to characterize the real heat transfer mechanisms. So the kinetic model, as I said before, is one reported in our research group that consider the total and partial oxidation of methane and ethylene and follows the Early-Riddle formalism. And finally, the reactor model consider this radioeffective conductivity. So the results. First, the velocity profile here shows the difference between considering fluid viscosity and an effective viscosity. Here, there is an over prediction of the velocity, and the mass conservation criteria was not reached, while in the velocity predict in our work met the mass conservation criteria and also gives a more reliable prediction of the velocity. For the axial heat transfer, the axial effective conductivity was estimated. It has a good prediction with experimental data, and also it is in the same magnitude order from other axial effective conductivity reported in literature. For the right temperature profiles, first we follow an industrial scale packet reactor experimental data from our research group, and we tested those approaches considering plug flow, considering fluid dynamics, and considering fluid dynamics with the pseudo-local parameter. Here you can see that the pseudo-local parameter has a better description of the experimental data. So this could give us more confidence on to use this parameter on the reactor model. So here we also tested it in a bench scale reactor and at several particle Reynolds, and also the local radioeffective conductivity has the better description. So the reason why there is the local parameter has a better description is because it decreases while it's approaching to the wall zone. So it's the temperature gradients here are higher, so the conductivity is lower. And also in the core zone, the trend follows the same velocity profile that here is in a dotted line in gray. So finally, the reactor model results are presented here. The yellow lines are considering plug flow. Here, the continuous lines are the prediction from our work, and the dashed lines are from literature. The difference between both is because in our work, we estimated the parameters using weighted or regression method, while in literature is not follow that kind of method. We put more attention trying to describe the temperature gradients in the wall zone. Also, you can see the difference between the approaches which use fluid dynamics, but mean parameters and local parameters. The difference is not so much big, but the hotspot it's predicted approximately 0.20 meters after the other approach. This can be seen as an effect of the pseudo-local radioeffective conductivity that captures in a better way the radial heat transfer resistances in the zone near to the wall. So with this, the conclusions and future work. Well, here the velocity profiles obtained considering the effective viscosity and reaching the mass conservation criteria has a better description of the velocity profiles within the bed and has no overprediction. The use of the pseudo-local relative conductivity provides a better characterization and also eliminates the cross-correlation between the relative conductivity and the wall heat transfer coefficient. And well, the simulations of the reactor shows a significant difference between when low flow is used and when dynamic fluid is used, which fluid dynamic shouldn't be neglected for this kind of reactor models. And also the difference between considering pseudo-local and mean relative conductivity shows that the better description of the relative conductivity must be considered for further models. And the future work is that this reactor model should be tested for a reaction that is now industrially, because our case of study is a promising reaction that has been scaled up at the industrial level. So, well, finally, I would like to thank to the LIR group from the Metropolitan Autonomous University of Mexico, also the CONACYT, to fund this project, Ghent University and the LCT, and the people from the Chem Reactor to let me share this progress made from our work. So, from my side, that would be all, and thank you very much.
Thank you very much, Alejandro, for your very nice talk. We have time for one quick question. Yeah. Anyone from the audience?
Yes. May I ask?
Yes, of course. You're welcome.
Yeah. Thank you very much. What I didn't find in your presentation is the effect of heat transfer on the target product formation. So if your reactor is targeted on the production of ethylene from the oxidative dehydrogenation of ethane, I would be very appreciated if you could show us how all those thermal conductivity issues affect the production of the target product.
Oh, okay. You mean, for example, the conversion of ethane? Well, in this case, GL of ethylene? Or...
Yeah, right.
Well, I didn't show it in the presentation. Yeah. No, I'm not having that information yet. But yeah, for sure, I have the simulations of the effect of this of the several heat transfer approaches in the prediction of the ethylene production. Yeah, and if you would like, I can share that information.
Okay, thank you.
Sorry.
I think that Professor Kopyczynski also has a quick question for you.
Yeah.
Good morning, Alejandro. Yes, thanks for the presentation. Yeah, I was wondering about the solid temperature. So because it's an exothermic reaction, so the solid temperature is significantly higher than the gas temperature. What are the estimated differences you have?
So yeah, like I mean the control temperature of the reactor, or
no, the solid. That's actually, you see it, the solid phase, right? You have a temperature minus T as surface, because when you put a thermocouple inside a reactor, you usually measure the gas phase temperature, but you also mentioned the gas phase. But highly exothermic, the solid, the catalyst temperature is significantly higher, but you don't measure it.
Okay,
but I guess you calculated it for your reaction progress. Do you have any estimation? What is the difference?
Yeah, well, it's kind of hard to measure. I mean, the difference between the fluid and solid temperature between both phases. I mean, we follow the assumption that there is no significant difference between both phases. But of course, this is something we need to consider for further work.
Okay, gracias.
Okay, great. Thank you, Alejandro, for your very nice talk and interesting answer. And we should now move to the next talk The next talk will be given by Professor Jan Kopyczynski from the McGill University in Canada. And the title of presentation is CO2 methanation and reverse water gas shift reaction, kinetic study based on in situ spatially resolved measurements. So please.
Yeah, thanks so much. Good morning or good afternoon to Europe and further down to Asia. So today in the first talk, but also in the second talk, we talk about a reactor system, a catalytic plate reactor that has a spatially solved in situ capability to measure gas composition profiles as well as catalyst surface temperature. And we use that to determine the kinetics for the CO methanation reverse water gas shift. So I guess a lot of people they have already learned in the last couple of years that this is a highly sought after reaction and of interest. So I don't really do a big picture, review about that reaction. I directly jump into the reactor that have been developed. Actually, the first version was developed at the Pascal Institute in Switzerland, like more than 10 years ago. And since arriving at McGill, we did a 2.0 version, let's say. And simply speaking, it's a channel reactor. It has approximately, if you see my mouse moving, I don't know if you see, it's approximately 10 centimeter long, 4 centimeter wide, and a half a millimeter in height. And the bottom is coated with a catalyst. The gas comes from the left, goes over the catalyst coated bottom plate. And we have here a small capillary. Maybe I go to the next slide. And the capillary is approximately 500 microns in diameter and has a very small hole laser drilled at the site, which is essentially moving and sampled with the MS. We also have some second channels, because you can imagine if you have an exotomic or any reaction that is above, let's say, 300-400 degrees C, the glass plate, we lose a lot of heat. So we added essentially the second channel counterflow hot argon just to avoid a huge temperature change in the 5 millimeter. This is, for example, one of the adjustments we made compared to the 10-year-old systems. The other thing, the capillary is essentially supported on two places, on the left and the right. So it's always at a certain, at a certain height above the catalyst. So imagine in the old setup in Switzerland, we had just the end capillary, which would essentially hang down. Okay, so what kind of catalyst, what kind of plate did we use for our reaction? So here's a small schematic, 10 centimeter, and you see not everything is essentially coated. The first either 10, 15, or here 30 millimeters is not coated. And then we coat our catalyst. We used Johnson Matthey catalyst, other commercial catalyst, but also our own. In this case, it's a 38% nickel on alumina, specific ordered mesoporous alumina. And we achieved very homogeneous coatings, but we also investigated other coating methods like dip coating, spin coating, and you name it, we tested it. And also we did some SEM, TEM, and we see our catalyst, for example, has a nickel crystallite size of 2 to 3 nanometers. This has been shown, I guess, more than 10 years ago. It's the ideal size for the nickel crystallite for the CO2 hydrogenation. We also did some side view SEM to see the thickness of the coating and also if we have really nickel nicely distributed. So we use FEC alloy, iron, chromium, aluminum alloy as a support plate. It's rough itself, you can see it here, and coated with our catalyst. In terms of the coating, how homogeneous they are, we did some profile measurements, essentially a tip. It goes over the plate and it measures the surface roughness and the coating thickness. So we used catalysts, they're 45 microns in size or sometimes even smaller than 10. For the 45 microns catalyst, we achieved a homogeneous coating with the thickness of like a 40 to 60 microns and a constant catalyst mass distribution. This is very important because we need to take the mass distribution into account. Other reactor concepts, they do partially soft measurements. You might not know the catalyst mass distribution, but you need it in the modeling. Okay, enough from the reactor and the catalyst. Let's go into the kinetics and the data, right? So we claim that we did the largest kinetic data set for the CO, CO2, and reverse water gas shift. So we tested various flow rates, various composition, hydrogen, CO, CO2. We add also methane, water, and changed the temperature and the pressure respectively. And you see, we claimed actually we have gathered 45,000 gas concentration data points, right? And every 3 millimeter, we also have the catalyst surface temperature, which we show you some data. So imagine we have the reaction like CO2 and to methane and CO to CO2 to CO reverse water shift. We have essentially 5 species, argon excluded, so 45,000 divided by 5. So essentially, it's like not more than 86,000 data point per gas species. So that is huge. But what we see here is, for example, for a standard case, 350 degrees C, 1 bar. And what you see is the length, the concentration, the first 10 millimeter from -10 to 0, it's the uncoated area where hydrogen and CO, nothing really happens. And once we go over the coated plate, you see hydrogen and CO2 are consumed, whereas methane and water are produced. And we also see slightly 0.5% CO produced. Right? And we did really every millimeter data point. You can imagine here's the length 48 millimeters. So we have already like a 48 data points per gas species, right? Imagine most of the people that have a packed bed reactor, right? So they have one experimental data point per one data point per experiment with the end of pipe solution. We already have here 58 data points. We also, with an infrared camera, we measure the real surface temperature. So that's where our reactor is optical accessible with quartz glass plate, and we use the near-infrared camera measure the surface temperature. And we see it's very homogeneous. It's a highly exothermic reaction, negative 164 kilojoule per mole. But we see there's maybe ±1 Kelvin temperature difference. I will show you later a picture how it looks like. And every day, actually, Jose, who was a PhD student, now the postdoc and PAC, they did all the experiments. So we overlay 3 experiments, the base case every day. Well, when we run one plate inside, we repeated the base case to see if the catalyst deactivates. And these are 5 or 3 experiments overlaid perfectly with each other, which means there's no catalyst deactivation. And we can use those profiles for our kinetic assessments. We also added higher temperature. As expected, hydrogen is increased further. Now we have more methane, more water produced. But also what we see, what you cannot really measure in the end of pipe measurements in a pet bed reactor, that CO is increasing in the first 10 millimeter and then is stabilizing and then it's actually decreasing, right? So I must say this catalytic plate has approximately 100 milligram of catalyst inside. Typically the same weight you put in a pet bed reactor. But we really measure the CO increase due to the reverse water gas shift. And then we can actually argue the CO decrease is more likely due to the CO methanation rather than the water gas shift and then CO2. Anyhow, I didn't vote here the CO methanation. We did also high pressure. So it's even faster, the hydrogen consumption and the CO2 consumption. And here we slightly also detect the first exothermicity, approximately 3 Kelvin increase, but we still consider this isothermal in terms of our modeling, right? And the higher the pressure, essentially the reverse water gas shift is also more suppressed, so the CO goes down. Now we have gathered all this data point. I just showed you a very small space what we actually have. And here's more like a video. We also tested a synthetic biogas. Let me just play the video. So what we added is methane and CO in the ratio of 60 to 40 and added 5 times more hydrogen than CO2. And again, over the non-coated area, kind of the purplish line, no reactions happening. And over the yellow line, it's hotter. There's a small exothermicity, but still constant. Hydrogen is converted and water and methane is formed. We see a slightly hot spot due to maybe the thermocouple, due to the heating elements we had below. But we could really measure the catalyst surface temperature. If you just poke a thermocouple inside, you measure the gas temperature, which is maybe like 5 Kelvin or 10 Kelvin less. Okay. In terms of the CO2, CO methanation reaction mechanism, there are a lot of mechanisms out there, but we gathered this 45,000 kinetic data points, which we could share if of interest, and somebody could come up with some models and fit the data. So we also developed some models. We actually created 20. So the simplest one, let's say CO, you abstract 2 carbon oxygens, and then you add 4 hydrogens, right? You have essentially 6 elementary steps, and each of them potentially could be a rate determining. The other mechanism is proposed. The CO bond is rather strong and needs maybe in hydrogen to lower the CO bond dissociation. So it's the hydrogen assisted, where the first and the second CO, it's helped with hydrogen to actually close the bond. Or we have kind of intermediate, which argues the first CO bond is rather simple, whereas the second CO bond is difficult to cleave, and we need a hydrogen to do so. You can design more than 20 different models. We did that and combined them essentially in a generalized Lange-Wünsch rate expression, depending on A, B, C, D. That is a different model, different assumptions. And we also included a KC, which is indicative of a carbon surface species that is in a rate determinant. That it could be a C, it could be CO, it could be CH, it could be COH, and so on. What you name it, what you propose. We also think that hydrogen is dissociative adsorbed and water is an OH. But we just gathered or proposed 20 models. But by all means, if you have another 20, we can still fit them in our model. It's a simple, let's say, two-phase model. Two-phase, I mean, we have the bulk phase with the convective flow, potentially axial dispersion, a mass transfer to the catalyst surface, which essentially include our catalyst weight distribution, which we measure, we know, and your reaction, right? Your proposed reaction mechanism. And we used essentially Athena Visual Studio and the Bayesian S-theorem to estimate for each of those models the parameters, right? So here you see kind of the summary. We minimize the objective function, and we see 2 models have the highest probability, right? With like 60% and almost 40%. The rest, statistically, based on the Bayesian theorem, are negligible, right? So also the objective function are much higher, right? And going in those 2 models, what do they propose? One model assumes the rate determining step for the CO2 methanation is the second CO bond cleavage, right? That is hydrogen assisted. And the other model that also fits very well is the hydrogen assisted CO bond cleavage for the first CO. So you essentially have here a formate or formula species. So both of them are statistically equally well described, but we try to see which one is essentially better in the grand scheme of things. So this is here the model 11 that assumes the second CO bond cleavage is the rate determining step, whereas the other one, the first CO bond cleavage, that both are hydrogen assisted. So how we can check those things, the surface species, we did later, I will show in a minute, a drifts measurement. But at first, let's put some parity plots in here. I actually claim we use 45,000 data points. That's true, but for the CO2 methanation reverse water shift, we only use 21,000 kinetic data points. We also did CO methanation and combined CO2 methanation, which are currently being essentially studied to make a unified model. So the fit is really good, right? You can argue, okay, it's plus minus 50%. Usually, sometimes you see it's perfectly on the line when other people do models. But again, we have here 21,000 data point and over a rather broad temperature and pressure range. So as I mentioned before, we try to elucidate, do we actually see those carbon surfaces or the CO or the formates on the surface? And yeah, we do. We did some drifts measurement under reactive conditions with the collaboration with the University in Bremen. And we actually see under reactive condition temperature programs at the beginning, the light gray line, it's 100 degrees C is going up steadily to 350 degrees C. Let's maybe going from the left-hand side, we see some OH group, right, either from the water or from the alumina. Then It's a very small peak, but above 300 degrees C, we see methane formed. Of course, this is our big CO2. And we see formed essentially our sorry, hydrogen carbonate or monadate carbonates, CO2 absorbed either on a oxygen vacant site or an OH group from the alumina. But nevertheless, we also see our formate and the COH. So both of them, we do see both of them have actually been predicted or proposed and kind of proven. Based on the model, it seems the peak for the formate seems a little bit higher than the one from the CO, right? So we still cannot say if model A or model B, so the two best models, which one is better. But nevertheless, we can say that the improved catalytic plate reactor is suitable for kinetic data collection, which will, Varun in the next talk will actually go more into detail. And we claim we have the largest data set for that reaction. We also can do other reactions, but still we are not really sure which of the weight determining step is actually the best one, because drifts as well as modeling propose two of them. But again, you can propose other reactions and or other proposed models, and we can fit them with the same data. Okay, so in conclusion, there was this, and I want to, of course, appreciate all the work that's been done by my students, especially Jose and Pak. And this is our group, and also for the financial support from NSERC and Coscienzas and University of Bremen. And of course, I'm now available for any questions you might have.
Thank you, Jan, for the very nice talk. The paper is now open for discussion. I see a question from the audience, so Professor Schildauer, please.
Yeah, so Jan, many thanks for the very nice talk.
Yep.
So now you're back. Okay, I have a question for you. If I look at your two models, right, most probably slide 19 or 20 or something, where we see the equations. No, yes, that one. Okay, now if we look at the pressure dependency of the methanation and the water gas shift, right? Then my feeling is in the model 11, then it's half order in CO2 for the methanation and first order for the reverse water gas shift. In the other model, it's first order in both of them. So that actually would imply, if I make a strong change of the pressure, that I should see changes in the selectivity.
We saw, right? Especially the higher the pressure, the either you can assume we produce less CO, right? So, but I don't know if the reverse water gas shift is suppressed or the reverse water gas shift it's higher, but then the CO methanation is faster, because what we haven't included here is the third reaction, because we see CO goes down, right? But based on our model, which is essentially not the best assumption, when CO goes down, it's converted. It's most likely not water gas shifted and then CO2 methanated. It's most likely CO methanated, right? So ideally, we should take into account the third reaction. So this is what we're also doing, essentially combining them. So similar what Sue and Fromond did in the 89 paper, what most of the people use for the three reaction. But again, they did steam forming water gas shift. They do all independently. But when we do CO methanation inside, so what is now the big question, Tilman? This is something you can help us. Is then the surface, like the CO, is this partial pressure dependent of CO2 or CO? Or do we need a second carbon species in the adsorption term? This is something we try to figure out, but let's talk.
Okay, good. Let's do it another time. Thank you very much.
Yeah.
Okay, thank you again, Professor Kopyczynski, for your very nice talk. Due to time constraints, we should now move to the next talk, which also comes to the same group in the University of Montreal, McGill University, and this is a joint contribution with Politecnico di Milano. The paper will be presented by the PhD student Varun Surendan, and it is titled Improved Catalytic Plate Reactor Design for High Quality Kinetic Data Generation Using Experiments and CFD Modeling. So,
hello.
Varun, floor is yours.
Hello, everyone. Is my screen visible at your end?
Yes, and
thank
we hear
you.
you well.
Hello all. In today's talk, I'm presenting an investigation into the flow phenomena in the catalytic plate reactor that was presented in the earlier talk. The primary objective of this study is to develop an understanding into the geometrical aspects of this reactor, as well as develop operational guidelines for using this in-house reactor for generating high-quality kinetic data. As shown in the earlier presentation as well, we see the PNID of the catalytic plate reactor here. The primary reactor is essentially a rectangular channel reactor with the dimensions of 100 millimeters in length, 40 millimeters in width, and a height of 5 millimeters. The bottom surface of this reactor is coated with catalyst, and the top layer is constructed from quartz glass to basically provide optical accessibility to the IR camera. Through this camera, we are able to generate catalyst surface temperatures while the reactor is in operation. Also here we have a continuous capillary as shown in the middle of this diagram, which has a capillary port of 250 microns that can measure the local local species composition so as to get a good picture of the local conversions. So going ahead, here we see a side view of the catalytic plate reactor. We have two channels shown here. The bottom channel is a reactive channel with the sampling capillary as well as the catalyst coated layer. And the second top layer, which is primarily used for maintaining isothermal conditions in the system. So as part of the study, we are trying to answer certain critical questions regarding the operation here, like do the sampling capillary have an influence on the kinetic data that is generated from this equipment? What could be an optimum range of operation for this reactor? Also, is there an influence of orientation of the port, whether if it is faced downwards or sidewards, could it impact the composition measurements? And also, how long would it take for the profiles to develop in the system? And finally, we are trying to compare it with the earlier generation open-ended capillary model or capillary CPR so as to evaluate its performance. Going ahead, so the chemistry studied here is CO2 methanation process. So primary two reactions that are incorporated here include the exothermic CO2 methanation reaction and the endothermic reverse water gas shift reaction. And this is incorporated into the CFD solver by means of Langmuir-Hinshelwood kinetics. And this is done with the help of a customized catalytic foam solver. And this is basically a heterogeneous catalytic reaction CFD solver that uses open foam framework for implementing the surface reaction process. And this has been a specific customized solver for this. Our catalysts have been developed by Shape Group at Politecnico di Milano, and that has been used for this study. Coming to the domain of the model here, we see the primary domain. It consists of three main regions: the central reactor domain, which is 100 millimeters in length, and the inlet and outlet zones, which are essentially identical, with each having 3 distributor channels and a manifold. As we see here, the inlets are located at the either end of the manifold. And also, since these 3 distributor channels are present at 3 different elevations, we don't have a symmetry of domain here, and hence are forced to use the entire domain for our simulation studies. And in addition to that, we are also incorporated the capillary along with the capillary port in this domain. Coming to the assumptions that have been used here, primarily the entire domain wall have been defined as an isothermal condition based on our knowledge that we got from the experiments. As we saw, the temperature variation was found to be less than 3 degrees Celsius over a range of experimental conditions. Also, we are not solving for flow inside the sampling capillary, and the suction created by the sampling capillary is created by defining a volumetric flow rate on the sampling port face. In addition to that, we have also not modeled the catalyst layer thickness in the current model. Going ahead. Coming to the model inputs, the current table shown here shows the range of experimental observation range, where we have varied the temperature between 360 to 420 degrees Celsius, and the bulk flow rates between 100 and 300 normal milliliters per minute have been studied. And the capillary suction between 2 to 10 milliliters per minute have been evaluated as here. And for both the plates considered here, we have an average catalyst load of about 100 milligrams. With respect to the mesh, the final selected mesh for the study has a cell count of 10 million cells and has been generated using Snappy Hex mesh. And a mesh sensitivity study was performed to generate mesh independent results, and the variation of mesh size was done between 4.7 million to 19 million cells. And the same standardized approach was adopted for generating meshes for the sideward as well as upward facing CPR models and also the open-ended capillary model. So now I'm presenting an experimental validation where we compare the experimental observations with the model predictions. This is done by noticing the axial species composition along the length of the reactor. So the case shown here has an H2 to CO2 ratio of 5 and a total flow rate of 150 normal milliliters per minute. We see in this plot the gas mole percentage along the entire length of the reactor, and it is shown here that the catalyst coating is present between 15 millimeters and 90 millimeters of this reactor. We see that about 55 mole percentage of hydrogen and 11 mole percentage of carbon dioxide enter the system, and while reaching the catalyst coated region, react to form products including methane, carbon monoxide, and water. Now overlaying the CFD modeling results, we see that the model predictions show a reasonably good agreement with the experimental observations. And now on the upcoming slide, I'm presenting a similar validation for a different case. In this, the difference here is that the total bulk flow rate has been reduced to about 100 normal milliliters per minute, as well as the H2 to CO2 ratio has been changed to 4. The plot has been presented here, which shows the variation of mole percentage of the species along the length. And what we see here in terms of prediction from the CFD also is in line with our earlier observations. The one point to acknowledge here is that we do observe an offset with respect to hydrogen, and primarily we believe that this variation that we see here is primarily caused due to the high diffusivity of the hydrogen species and also some the closure of balances that could have happened during the experimental process. Going ahead, now trying to identify the different effects in the system, starting with the first aspect, which is the effect of distributor channel. So basically, the sampling capillary is present in the central region, which occupies some space in the inlet distributor channel as well, and hence it diverts 75% of the flow through the 2 outlet laterally located distributor channels. And this kind of results in a recirculation region in the inlet domain, and this can be clearly seen in 300 normal milliliters per minute flow case, as we see a recirculation zone being created in the inlet domain, which has almost reached the point where our catalyst coated region starts, which is at 15 millimeters down the line from the starting of the reactor domain. When we reduce the total bulk flow rate to about 100 normal milliliters per minute, we observe that this effect is suppressed and the flow stabilizes significantly earlier than reaching the coated region. Now, in order to understand further how this influences our sampling capabilities, we need to observe how the flow around the sampling zone is there. To do that, we have actually extracted the axial velocities along a straight line on a plane that is located exactly vertical to the sampling capillary. And what we see here is the velocity profile of axial velocity along the entire length of the reactor. The profile here can be broken down into 3 zones, essentially zone 1 and 2 that are related to the inlet and outlet of the reactor, whereas a zone 3 which corresponds to the region which is coated with catalyst. On increase of bulk flow rate, we see that the flow stabilization requires certain additional length into the domain, and even for the highest flow rate of about 300 normal milliliters per minute, we see that the flow develops by about 30 millimeters into the reactor domain. Going ahead. In terms of suction, the suction is primarily driven by the mass spectrometer that is attached to the CPR setup. And as per the manufacturer, this suction is defined at the rate of 1 milliliters per minute per bar of operating pressure. So for a kinetic experiment that is conducted at 4 bar operation pressure, we will have a suction of about 4 milliliters per minute. So in order to develop a qualitative understanding of this suction, we have actually generated streamlines from a line source that is located about 0.1 millimeter above the bottom plate, which is coated with catalyst, and about 2 millimeters upstream of the sampling location. What we see here is basically a conical region of influence generated as a result of the suction from the sampling capillary, and the top views of the same have been shown in the upcoming slide. Here we see the top view of the streamlines generated from the line shown earlier. What we see here for this specific case of 2 milliliters per minute suction is that there is a region of about 0.5 millimeters on either side of the sampling port, which is under the influence of the suction. And as we increase the suction to 4 and further to 8 milliliters per minute, we see this region expands to about 1.5 millimeters on either side of the sampling port, as well as 2 millimeters downstream of the port. so whereas in real life situations, we will not be operating in this level of suction, but here, even at this range, we can observe that the entire range of influence is in a way restricted to a region of about 2 millimeters on either side from the sampling location. In order to quantify this, we have selected certain vertical lines located just below the sampling port. Here we see 3 lines located at 1.5 and 2 millimeters below the sampling port, and the velocity vectors have been generated on these locations, and these have been colored with mass flux at those locations, which are in upward direction. And what we see here is that the mass flux at y is equal to 2 mm is almost 100 times more than what is existing on the plate, pointing to the fact that the mass being sucked in by the sampling port is essentially the mass that is present in the vicinity of it. And hence, if we are not in a mass transfer limited range of operation, we will essentially be getting an averaged value of composition through the measurements. Even at a elevated suction of 8 milliliters per minute, we see that the ratio of 100 stays the same, even though we have higher values for the mass fluxes at each of these elevations as shown here. Now, in order to understand how the species profiles develop along the length, here I have presented the isocontours of CO2 mole fraction along the length of the reactor, and also a slice view along a central plane. Here we can clearly see in the slice view that the CO2 profile has a curved nature, primarily based on the fact that the CO2 is getting consumed on the catalyst surface located at the bottom of the plate. And on understanding how the variation of the species composition is there along the width and height of the system, we see that there's a maximum variation of about 0.4%, indicating that this essentially, the composition that we are getting at this location would not really depend on how the capillary is oriented. Even if we have a sideward facing or upward facing capillary, we would essentially be getting almost similar composition information from experiments. So in a way, saying that the orientation of sampling capillary port will not have a significant influence on the sampling capabilities of this reactor. Further ahead, in the last slide, we discussed how the variation of composition was along the width and height of the reactor. Now on this plot, I have tried to capture how this composition varies along the length of the reactor. Here we see 2 lines, the first one being the sampling zone line, which is a straight line located exactly below the sampling capillary, whereas the other one, which is an identical line offsetted to match its location in a laterally located channel. And we tried to match the compositions of CO2 at these 2 locations and along with the experimental observations. So in this plot, we see the mole percentages of CO2 along the entire length of the reactor measured from the sampling port. Now overlaying it with the CFD model inputs from those 2 locations, we see that the red line from the sampling zone as well as the blue line from the reference zone almost overlap with each other, proving the fact that the measurements done by the sampling port at that location is a reasonably good estimate of the axial of the composition of CO2 at that axial location in the CPR reactor. Further ahead, here we have tried to compare the performance of the current continuous capillary CPR reactor with the open-ended one. In the open-ended reactor, the primary difference, as we see here, is that we have a capillary that is entering from the lateral end of the reactor and kind of moves in and has an open end through which the measurement is taken. As we see here, we have tried to generate velocity vectors at certain horizontal locations below the sampling capillary as well as 2 vertical locations upstream of it. We see that the influence of the capillary is minimal below it, and also the influence is restricted to about 0.5 millimeters upstream of it. This reduced effect of the sampling capillary suction is primarily due to the same direction of the both bulk flow rate and the direction of suction into the capillary. In a way, it points to the fact that in current situation, the open-ended capillary would be advantageous in a situation where we have higher flow rates, but we need to be aware of the fact that in such situations, a similar design would be prone to oscillation or bending that may occur due to the high rate of flow there. So coming to one more design aspect which was evaluated was basically introduction of dummy capillary in the system. What we did here was, as we saw, almost 75% of the flow was entering the system through the 2 outer distributor channels. We plan to introduce 2 dummy capillaries in the system so as to overcome this maldistribution here. And as we expected, we saw a very good stabilization of flow in terms of performance, and we almost reduced the maldistribution to below 1% by introduction of this design change, and hence could be a possibility in the upcoming generation of the CPR to be have this feature so as to overcome the maldistribution between the three channels into the system. Now coming to conclusions of my talk today. So basically the key outcome of this analysis was the sampling capillary effect was quantified, and it was observed that for the current range of studies, the effect of sampling capillary port was restricted to a location of about 2 millimeters on either side of the sampling location. And the orientation of the capillary port did not have a significant influence on the sampling effect. Also, almost 70% of the length of the catalyst CPR reactor can be used for kinetic data extraction. And a flow rate of less than 200 milliliters normal per minute would be optimum for the current kinetics. And both open-ended as well as the continuous capillary modes of operation perform similarly in the current range. And finally, introduction of dummy capillaries could be an option that could be adopted for the upcoming generations of CPR reactors. I would like to thank everybody for your time, and thank CPE and SHAPE members for their help, and also MITEX and ENSER for the funding, and Compute Canada and Chineka clusters for the computational resources for this work. Thank you.
Many thanks, Varun, for the very nice talk. The paper is now open for discussion. Is there any question from the audience? If not, I have a couple of curiosities. The first one is, what is the maximum pressure you can use in your device?
So this CPR reactor has been tested up to 10 bar operations, and okay. In the simulation, I have gone up to 4 bar for the simulation studies.
Okay, and do you expect the reactor to be used also in the case of three-phase reactions?
So you mean introduction of liquid along with the system?
Yeah, for example, or do you think that the system can be used also for reactions forming products in both the gas and the liquid phase? Or do you expect that the situation will be significantly different with respect to the one you studied?
Yeah, the system would be different in terms of the properties, but I believe since we are at very low Reynolds number ranges in terms of operation in the current study, I think that would significantly change with introduction of a separate phase with different properties. So that could lead to different observations from what we have with the current study.
Okay, thank you very much. Any further questions from the audience? I can't see any questions, so if there are no more questions, we can thank Varun again for the very, very nice talk. And we can move to the next presentation. So the next presentation comes from Mexico, will be given by the PhD student Luis Antonio Ramos Huerta from the Metropolitan Autonomous University. And the paper is titled Kinetics coupled with the radiative transfer under visible light operation reactions on graphene oxide. So, Luis Antonio, the floor is yours.
Thank you very much. Can you see my slides?
Yes, your slides, and we hear you well.
Okay, perfect. So, good day, everyone. My name is Luis Antonio Ramos Huerta. Thank you very much for the introduction. I'm going to present you an ongoing research from with the group I'm working in. It is entitled Kinetic Evaluation Coupled with Radiative Transfer Studies, and Dr. Castillo and Master Gomez have collaborated in the development of this research. So the presentation will cover why we are researching this topic with the motivation and the introduction, how we are approaching the research by defining the methodology, and what we did and obtained by showing our results and conclusions. So let's start with why. Chlorophenols are a group of chemicals in which chlorine has been added to phenol. There are different types of chlorophenols, and these substances are listed by the US EPA in the Clean Water Act as a group of priority toxic pollutants due to both their toxicity and their difficulty to remove from the environment. Chlorophenols were used previously as pesticides, herbicides, disinfectants, antiseptics, wood preservatives, and others. They can also be produced by means of chlorinating raw water while producing drinking water or when bleaching wood pulp to produce paper. Thus, chlorophenols are readily available and are a source of concern as they are probable carcinogens, cause liver and immune system damage, as well as several other conditions. In this regard, it is of interest to implement treatment methods that allow water purification and in turn diminish pollution and environmental damage, as well as human threats. Conventional treatment methods such as biological, physical, or thermal have been previously implemented. However, some challenges have been posed as chlorophenols have biocidal properties that make them good antimicrobials. Thus, biological treatment requires long residence times. Furthermore, physical or chemical methods often result in effective or require post-treatments to remove the pollutant from contaminated environments. On the other hand, thermal approaches might worsen the issue as other hazardous compounds might be emitted. As a result of these difficulties, the application of oxidation techniques has been implemented, being photocatalysis one of the most efficient advanced oxidation techniques. And what is photocatalysis? The photocatalytic process starts with the excitation of one electron from the valence band into the conduction band of a semiconductor. This occurs thanks to the incidence of a photon of enough energy that allows the electron to surpass the band gap. This creates a charge separation that allows the system to react. As we can see, light is a key ingredient to the process, and without it, we would not have reaction. So we must study light, and above all, we have to understand how it works and interacts with our systems in order to determine how much of it is actually used by the catalyst. In this regard, there is this equation, the radiative transfer equation, which describes the change of light intensity with distance. It considers a term that includes the absorption, and the dispersion called beta, an emission term which is usually neglected because applications in photocatalysis usually are underneath 40 Celsius degrees, and a term that is called the phase function that describes the photon input from other scattered directions together along with the function of light, the fraction of light that is scattered called albedo. Beta and the phase function are the optical properties of the catalyst, and we aim to determine them. Previous researchers have determined these optical parameters, but their values cannot be applied to other systems or to other scales because certain considerations have been determined, especially in terms of the phase function. Usually, isotropic phase functions or simplified 2-flux or 6-flux phase functions have been selected, or in its effect, they have been chosen a priori. For beta, Beer-Lambert law has been used, and sometimes its determination has not included backward scattering. You can see here, affecting not just one but the three parameters. One approach that has tackled one of these problems has determined the phase function with a Heinze-Greenstein equation, approach that solves the a priori chosen phase function, but has also incurred in the other points aforementioned. Besides having a strong solid position in their experiments, other researchers tried to overcome this issue by implementing a variable optical depth without changing the amount of catalyst. However, their reactor's complexity and scale left them with no choice but to take values from literature for beta and the G parameter. The complexity of the radiation transfer equation, which leads to the determination of the LBREA, renders simplified kinetic descriptions of laminar Hinshelwood or first-order type that do not include the radiation profiles. These type of kinetic expressions turn out to be useful only for the experimental systems where they were obtained. Therefore, the required kinetic models must be independent of the reactor configuration and based on the detailed reaction mechanism configuration, including activation steps by radiation and those LBREA, such as the ones presented by Marugan and Valadez in their own research. In this work, we present an in-depth study that relates the interaction among kinetics and radiation transfer and its application in the degradation of chlorophenols. The optical properties of the material are obtained via an in-house methodology. A kinetic expression is then derived from charge separation at the moment of semiconductor excitation. This is the driving force of the reaction that generates holes and hydroxyl radicals, the main species responsible for the chlorophenol degradation. So passing on to how we do this, an in-house developed experimental system, as the one shown in this upper figure, is just to determine optical properties. This setup allows scattered transmitted observations, scattered and transmitted, to be obtained, and with the help of specific surfaces determination, Macroscopic light balances are made from which optical parameters are determined. Once having these parameters, the RT can be solved. In our case, we use an stochastic Monte Carlo method that follows the algorithm in the block diagram to the right to deliver the LBREA needed for the kinetic evaluation coupled with radiation transfer. Continuing with the kinetic part of this research, we assess the importance of Holt's production in the reaction by carrying out a modeled reaction that qualitatively gives us information of the whole production. First, we make a solution of 5 ppm of indigo carbon, and we fit the solution to a custom reactor with a light jacket. The catalyst is added to this reactor setup, and reaction is followed for several hours. Afterwards, the same procedure is repeated, except this time 50 ppm of ammonium oxalate are added. And you might wonder, why is ammonium oxalate incorporated into the reaction? And the answer to that is that it works as a Holt scavenger, capturing the holes that would react with the organic compound and instead using them to transform it into carbon dioxide. Finally, a kinetic mechanism is proposed based on the state-of-the-art information in thermodynamics. Our initial mechanism included transition species and several unstable compounds. However, after a thorough thermodynamic assessment and some simplifications as the lumping of the organic acids production into an ionization reaction, we ended up with a compact yet sound mechanism for this degradation reaction. It is important to notice that, as mentioned earlier, Holt's and hydroxyl radicals are the main drivers of the reaction, and without them, there would be no reaction. Interestingly, these species are created only in the presence of light, hence the importance of coupling kinetics with radiation transfer studies. And finally, what we have achieved, we determined the optical properties of both the titanium dioxide and graphene oxide. The former under visible and UV light. We obtained a specific extinction coefficient of 0.78 and 3.9 per ppm per gram for titanium dioxide under visible light and UV light, respectively. The UV light values agree with previously reported ones in literature, such as a 4.5 value in Cabrera's work and a 1.3 value in the Puma's research. Furthermore, the trends in these works show that when shifting to wavelengths closer to visible light, the specific extinction coefficient value decreases rapidly, which agrees with the fact that in the present work, the specific extinction coefficient for titanium dioxide under visible light is 5 times smaller. Something similar happens with the albedo, where reported values range from 0.81 to 1 in the 375 to 400 nanometers range. Our albedo value is in the low range of this fraction. However, albedo is usually calculated from front dispersion observations only, which renders an overestimation of the parameter problem we overcame by considering lateral dispersion as well. In summary, our methodology delivers optical properties in a trustworthy manner, and that let us obtain the ones for graphene oxide under visible light, an extinction coefficient of 0.36 per ppm per gram, a low albedo of 0.135, expected due to the color of the graphene oxide, and an almost isotropic asymmetry parameter of 0.12. As for Holt's, we determined there is no photolysis of indigo carmine, and thus any reduction in the amount of organic dye was due to the presence of the catalyst. We can observe that for a reaction time of 6 hours, the initial concentration of indigo carmine dropped by approximately 80% when using graphene oxide, around 30% when using titanium dioxide, and about 5% when ammonium oxalate was added. It is important to mention that these results are under visible light, where titanium dioxide is expected to behave poorly compared to graphene oxide, as we noticed from the optical parameter results. However, the interesting part here is that when ammonium oxalate is added, there is practically no reaction, and if we remember, Holt's are the first species to interact with the organic compound to form intermediaries, but will then react with hydroxyl radicals or other species. But ammonium oxalate is scavenging these Holt's, and thus reaction is severely hindered. Regarding kinetics, a complete solution of the mechanism proposed was modeled, and experimental results from Chateau were taken in order to estimate the kinetic parameters of 4-chlorophenol degradation. As you can observe, the experimental results to the left have been reproduced to a good extent by the model, which results we can see in the right. In our case, we included the total degradation of chlorophenol into carbon dioxide and accounted for benzoquinone hydrobenzoquinone, hydroxyhydroquinone, as well as the full coupling with the radiation, the development of the model took into account charge separation, recombination, hole entrapment, and hydroxyl attack mechanisms, as well as competitive absorption. And to the right, you can see the estimated parameters for this model. This work led us to the following conclusions. First of all, a kinetic evaluation incorporating radiation transfer is definitely possible, and this research allows us to propose a step-by-step evaluation process. Radiation transfer analysis will yield optical parameters of the materials and the radiation profile of energy absorption. Thus, the step-by-step evaluation would begin by optically characterizing the used catalyst, followed by the quantification of holes production, as well as the quantification of hydroxyl radicals, which were not included in the present work. However, it is contemplated as future work, and the methodology development is currently underway. Once we have enough information, a kinetic mechanism should be defined considering thermodynamics and state-of-the-art kinetics along with radiation transfer mechanisms. Afterwards, the reaction should be carried out and analyzed. Once all the information is handy, estimation of parameters and validation of models should be made. We also have noticed from this work that even though photocatalytic reactor scale-up is still far away, progress can be made in that direction, and with fine-tuning of the methodologies and the implementation of some other aspects, it could be a reality that photocatalytic reactors are used for commercial applications with reliability. Thus, we paved the way with some points that we consider are needed future work for this to become true. First of all, we should include hydroxyl radicals quantification for applications of degradation in order to harness the most from solar power. We should transition to visible light-driven operations, and in this regard, we recommend graphene oxide as a promising material, not only because of its application in the degradation reactions, but because we have conducted some other experiments for photoreduction and we have had good results. Thus, this material seems flexible and efficient enough to tackle diverse applications, as we could see from the indigo chromin degradation and optical parameters results. And this is related to our next point, which is to assess other reactions, such as the reduction of carbon dioxide to produce methanol, for example, or the degradation of different pollutants. Finally, we believe that coupling these type of studies with mass transfer and incorporating a local LBREA profile, taking into account the impact of light and reactor geometry interaction, would be beneficial in this regard. This, in our opinion, would direct the way to be closer to an industrial scale photoreactors. And well, that was it. Thank you very much for your attention. Hope you enjoyed the presentation.
Thank you, Luis Antonio, for the very interesting talk. And the paper is now open for discussion. Do we have any questions, comments, remarks from the audience? I have a curiosity on the last point of the last slide, the future work. Yes. Can you give us more insights on what you're planning to do to couple mass transfer in the present work?
Yes, we have a local LBREA profile. We already have that. However, when we incorporate it into the kinetic assessment, we do it as an average, a mean LBREA. And we want to incorporate mass transfer to in a discrete way, like a local mass transfer profile, where we can say how much of the carbon dioxide is in each part of the reactor, and we can then couple that with the local LBR profile in that point, so that we can have a local reaction expression or value, and we would have like a field of reaction inside our reactor, and we would assess if the profile of light is actually changing a lot the extent of reaction along the reactor, or if we can use an average LBR total.
Okay, thank you. In the meantime, any news from the audience? Any question? Any comment? We have a few more minutes before switching to the next talk. So please feel free to ask questions. I'm just waiting some raised hands or some open mic and camera. Luis, we have 2 or 3 minutes more. Is there anything else you want to add to exploit this time we have?
Sure. We have been working in different types of reactions in visible light and invisible light. Our main focus nowadays is carbon dioxide photoreduction in order to produce methanol. We have made some advances in this regard. We have produced formic acid first, and from formic acid we have achieved a production of methanol. We are still in the fine-tuning of the methodology, but we believe it could be a success. We are using graphene oxide as well, and of course we would want to start scaling up these type of reactors, at least to a bench scale photoreactor. Similarly, we would want to start taking experiments under solar light to see if this could help us harness both visible and UV light, and thus further improve the reaction extent in this matter. So that's the work we are been doing at our group, our research group, which is the Laboratory of Catalytic Reactors Engineering at Universidad Autónoma Metropolitana in Mexico. So if you have any further questions or you want to talk a little bit about this, you can contact me at that email. And well, that might be it, I believe.
Yep, excellent. Thank you very much for your contribution and good luck for your work. We can now move to the next talk. The next contribution will also come from the Metropolitan Autonomous University of Mexico. The speaker is the PhD student Roel Hernandez Rodriguez, and the title of the talk, which is probably changed a little bit from the program, I can read from the slide, is on the derivation of microscopic model for hydrodynamics in fixed bed reactors with a low dT over dP ratio. Oh no, sorry. So we have switched the last two contributions. I was expecting now. Oh yeah, no, that's fine. Sorry, I had a slightly different program. So please, Roel.
Okay.
The floor is yours.
Thank you very much for the presentation. Can you see my presentation?
Yes, yes.
Okay.
We see
okay, thank you. Well, as was already mentioned, the title of this presentation is on the derivation of a macroscopic model for hydrodynamics in a fixed bed reactors with a low dT and dP ratio. Well, briefly, it is well known that the fixed bed reactors with a low dT and dP ratio are readily used to carry out highly exothermic reactions, and the main reason of this is because it promotes or it improves the removal of heat transfers along this kind of fixed bed reactors. Well, and one of the main characteristics of these kind of systems or fixed bed reactors is that it presents abrupt changes in the void fraction, which in turn generates rapid changes in the velocity profiles. Well, but in addition to this, the velocity profiles that take place in these kind of systems can determine the rate of heat and mass transfer along the fixed bed reactors with these characteristics. Well, therefore, in order to obtain an accurate prediction of the heat and mass transfers in these kind of systems, first we need to predict, first we need to have an accurate predictions of the average velocity profiles, and as was shown in a previous presentations. Well, to do this, we have two alternatives. The first one is using local models, which distinguish each of the phases involved in the fixed bed reactors. And in these models, the mass and momentum transfer are described by using local equations. Yeah. But this alternative has some problems. The first one is the geometry of the fixed beds are unknown. The geometries are unknown, but even if the geometries were known by using, I don't know, specialized software, these kind of systems are usually very large, which leading to obtain a disparity of characteristic lengths between the particles and the length of the tubes, which makes this problem or the solution of the local equations a high computational demand and problem. Well, that's why in many situations we need average models, yeah, which consider the fixed bed reactors as a pseudo-continuous domain, as shown in this figure. Well, and in these models, or in this approach, the mass and the momentum transfer is described by using effective medium equations, and these equations contain effective medium coefficients like the void fraction or the permeability or apparent permeabilities, and in some cases effective viscosities. But in this alternative, or in this context, one of the most widely used equation is what is known as the Navier-Stokes-Darcy-Forchheimer equation, which is shown in this equation, which is basically the Navier-Stokes coupled to the Darcy and Forchheimer term, which is shown in this blue square. Yeah, and this term is has the aim to capture the effects of the presence of the solid particles in the fixed bed. And to do this, we have some coefficients like the permeability, which is given by the Karman-Koseny equation. And we have another kind of permeability, which is given by the Burke-Plumber equation. And these two expressions are contain coefficients, in this case, and the alpha parameter and the beta parameter, whose original values were proposed for the alpha, for example, was equal to 150, and for the beta equal to 1.75. But even this approach, or even this equation, have some problems. The first one is that it was originally proposed semi-empirically, yeah. And the second one is that it was proposed for fixed bed reactors or fixed beds in general for a DT with a DT and DP ratio larger than 10. And that's why for fixed bed reactors with a low DT and DP ratio, it overestimates the velocity profiles. Thus, it needs, in many cases, it needs, or in many works, they estimates the parameters, in this case, the alpha and beta. Well, with this in mind, we can say that it is still necessary to develop effective medium equations, which provide a reliable predictions of hydrodynamics in fixed bed reactors with a low DT and DP ratio, but without the estimation of coefficients. Right. Well, with this in mind, the question to be addressed in this work is that if it is possible to derive effective medium equation to describe hydrodynamics in fixed bed reactors with a low DT and DP ratio that don't require the estimation of transform parameters, but at the same time capture the information from the local scale. Well, to answer this question, we consider the following problem. We consider the flow through a fixed bed, like as shown in the figure. The flow, the inlet is at the bottom, the outlet is at the top, and the work fluid is air at a temperature equal to 400 degrees centigrade, and the rho beta is the density and mu beta is the viscosity. And for this particular system, we have that the length, the characteristic length that has this system is L, the length, equal to 260 centimeters, and a tube diameter equal to 2.46 centimeters. And for the particle diameter is equal to 0.8 centimeters, which give us DT and dP ratio equal to 3.075. As we can observe, this problem is a challenging problem, not? And the question is how we can describe this model by using effective medium equation. Well, to develop the model, we proposed to use a methodology which is known as the volume averaging method. Yeah, this is a very well-known methodology to develop effective medium equations, but starting from the governing equations at the local scale. Yeah. In general, or briefly, we can say that this methodology, the general framework for this methodology consists of 4 steps. The first one is the statement of the local model. Yeah, it needs an averaging process as a second step. And for the third step, it needs the derivation of a closure problem, which allows us to predict the effective medium coefficient. And finally, we can obtain the closed macroscopic model. Well, to apply this methodology, we make the following assumptions. We considered that the fluid is a Newtonian fluid, which is denoted as the beta phase. We considered also that the solid phase is impermeable. In this case, is denoted by the solid phase. And we considered also that the flow is incompressible and take place under steady state conditions. Under these assumptions, the governing equations at the local scale, or in other words, the local model, is given by these governing equations. We have the continuity equation, the Navier-Stokes equation, and also we have the boundary conditions. We have the no-slip boundary conditions at the solid fluid interfaces. We have the inlet velocity, the boundary condition, and the outlet boundary condition. Well, with this in mind, to follow or to progress in this development, we introduced the following operators: this superficial averaging operator, an intrinsic averaging operator of a quantity defined in the beta phase, of course. And these, we have to say that these operators are defined in terms of an averaging domain. In this case, we took annular volumes, as those shown in this figure, which consist of a region occupied by the fluid phase and a volume occupied by the solid phase. And also we should say that these two operators are related by the Dupuit-Forch-Kramer equation, where epsilon beta is the void fraction. Well, with this in mind, if we applied these operators and additional development, we can obtain the following closed average equations. This is the average continuity equation, yeah? And we can see that it is similar to its local counterpart, but the interesting part is here, is the average momentum equation. Here we can see that in this new equation, or this average equation, we find 2 new terms, or two viscous terms, which are known as the first Brinkman correction and the second Brinkman correction. And the second Brinkman correction appears because or appears in system which presents spatial variations of the void fraction. But also we have an inertial term, and also we have a resistance term, which is in this case, as a result of the averaging process, this is the term which considers the presence of the solid particles. Well, we have two additional coefficients. In this case, the coefficient J and the coefficient H. In the first case is a total inertial tensor, yeah, and the second one, the coefficient H, is an apparent permeability. Yeah, in this case, as a result of the development, these are tensors. The first one is a 4th order tensor, and the second one is a 2nd order tensor. Yeah, and as we can see, these tensors are defined in terms of closure variables. In this case, the uppercase B is a second order tensor, and the lowercase b is a vector. Yeah. Therefore, in order to predict this coefficient or these effective medium coefficients, we need to solve, or we need to know these closure variables. And the method allows us to obtain the boundary value problem associated to these closure variables. Now that we have the closed form of this equation, we need to predict the effective medium coefficient. And as I mentioned, these coefficients are defined in terms of closure variables. We solved the boundary value problem associated to these closure variables in a representative domain of the fixed bed. And how we build this representative domain? Well, we take layers consisting of seven particles, as shown in this figure, and we put every layer one over the other, and each layer was rotated around the axial direction 30 degrees, and until we reach a unit cell or a representative domain. We solve it in this representative domain, the boundary value problem. As you can see, this is not the complete fixed bed reactor, but and with this, once we have the fields of the closure variables, we computed the effective medium coefficients in different positions along the radial direction. We can see the following profiles. For example, this is a two-dimensional profile of the void fraction in a cross section of the fixed bed. Yeah, as you can observe, it is periodic. And if we take a cut line from this two-dimensional profile, we can observe the following profile. We can see that we have two maximum values in this case. Also, we have two minimum values in the void fraction profile in the radial direction. Well, we compare these profiles with a widely used correlation, which provided by the clerk. And we can observe that our predictions are only similar near to the wall. This is here is located the wall, and this is near to the core of the fixed bed. Yeah, we have important deviation near to the core of the bed. Well, this is the apparent permeability. Yeah, this is the two-dimensional spatial variation, two-dimensional variations of the apparent permeability. If we take a cut line, we can observe the following behavior. We can observe also we have two maximum values and two minimum values, which are consistent with the void fraction. Well, this is for a Reynolds number, 1400. Yeah, a particle Reynolds number, and we also performed the calculations for other particle Reynolds number. As we can observe, these coefficients, it depends on the particle Reynolds number, and which means that it increases the permeability decreases with the values of the particle Reynolds number. Well, now that we have these coefficients, we are ready to validate our model. And to validate this or to perform this, we compared the average velocity profiles resulting from the solution of the effective medium equation that we obtained in this work with those obtained from averaging the pore scale profiles. It means that we first solved the local model in the representative domain of the fixed bed reactor. We can observe the following profiles, local profiles, where we can observe the presence of the solid particles. In general, we can observe that the larger values of the velocities are near to the wall, and the lower values of the velocities are in the core of the wall of the fixed bed. Well, with these local velocity profiles, we take different volumes and we apply the superficial averaging operator, and in different positions in the radial direction. And we obtained the following profiles. This is an example of the local profiles, and this is the average profile. As you can observe, many of the information, of the local information was lost, but this is because the averaging process. Well, taking these velocity profiles, we can take cut lines and we can observe the following. The following profile. As we can observe, we have two maximum values also. In one of them is near to the wall here, and the other is near to the core of the fixed of the bed. Yeah. We also computed these profiles for other Reynolds number, and as we can observe, or as we expected, that by increasing the Reynolds number, the magnitude of the velocity profile increases also. Well, now we are ready to compare these velocity profiles with those obtained from the resolution of the average model obtained from our methodology. Well, the black points are those obtained from the Porte scale simulations, and the red line are those obtained from the volume averaging method. As we can see, those profiles obtained from the volume averaging method are in good agreement with those obtained from the Porte scale simulations. Yeah, we also solved the conventional approach, which we mentioned is the Navier-Stokes Darcy-Forchheimer equation, and you can observe that this model overestimates the velocity profiles in two zones around the two maximum values, near to the wall and near to the core of the bed. Yeah, this happens for the three Reynolds numbers that we computed. Well, we also have the comparison for the average pressure profiles. Also, we obtained similar results with the red line, which is the volume averaging method results. We can observe that they are closer to those obtained from the Porte scale simulation. As a final analysis, we computed the magnitude of the term that captures the presence of the solid particles. And for the original values of the alpha and beta, as you can observe, we have the important deviations, yeah? And that's why we have important deviations in the average velocity profiles. We also computed this term for estimated values of alpha and beta reported in the literature, and we can see that even when we estimate this coefficient, we have deviations in the magnitude of this term. Well, as conclusion, we can say that we have derived a macroscopic model to describe hydrodynamics in a fixed bed reactor with a low DT/dP ratio, and this model can describe the hydrodynamic in a fixed bed reactor with a low DT/dP ratio. And this method allows us to predict the effective medium coefficients by means of a local closure problem. And the salient point of this is that the solution of the solution domain of this local closure problem is just a representative domain of the fixed bed and not the whole fixed bed. Well, thank you very much for your attention.
Thank you very much, Roel, for your very nice talk. And the paper is now open for discussion. Is there any comment or question from the audience? Please feel free to open your mic and turn on your camera to ask questions.
I have a question. Thanks for your presentation. How does your model will change or influence, for example, when you're taking reactions account with a huge volume change, right? Either the volume expands or the volumetric flow rate essentially decreases. And then in addition, when you have multiple or you have a catalyst particle distribution, you have now a perfect system, which it's in reality, it's not perfect, right? We have usually a rather, I don't know, or strong particle size distribution. Can you maybe comment on this? If your model will be able to account for volume change and reaction as well as different particle size distribution?
Yes, well, thank you for the question. For example, all the profiles that we obtained in this case, we fixed the size of the volume of the Auvergne domain, yeah, and this is for fluid mechanics. Well, the same volume that we use in this case, we should be used for modeling also the heat or mass transfer, not. But if we change the size of this Auvergne volume, of course, we expect that the profiles, all the profiles, not only the velocity profiles, will change. Yeah, if we increase the size of this Auvergne domain, probably the velocity profiles will reduce. Yeah, and of course it will influence the results that we will obtain when we are comparing with experimental observations. And a strategy to fix or to determine the correct volume in many cases should be based with the experimental devices, I think, because if we take, for the case of velocity, if we take volumes or images to measure the velocities, larger images, for example, in a PIV instrument, if we take large volumes or images, the volume that we should take in this methodology should be in accordance with that measurements. Yeah.
Okay. Yeah. Thank you.
Great. Thank you, Roy, again for your very nice talk.
Okay.
And we can now move to the last presentation of this session and of the conference. We remain in Mexico, in the Metropolitan Autonomous University. The speaker is the PhD student Alberto Hernandez Aguirre, and the paper is titled DNS-based effective medium model for the compressible flow in a fixed bed reactor with low dT over dT. So please, Alberto, go ahead with your presentation.
Thank you for the presentation. Good morning for all. I will talk about the most recent publication of the work, titled Framing a Novel Approach for Pseudo-Continuous Modeling using Direct Numerical Simulation, or DNS, Fluid Dynamics in a Packet Reactor. In this work, we try to connect the local scale with the pseudo-continuous scale. The local scale is described by the using microscopic Navier-Stokes equation, while that the pseudo-continuous scale consider that the solid and the fluid phases have a single pseudo-continuous phase. Here, the properties of the solid and fluid phases are considered throughout the use of effective coefficients. Here, the hydrodynamics is described by using Navier-Stokes equation coupled with a D term that consider all resistances due to the fluid, due to the presence of the solid. Here we determine the so-called fluid dynamic descriptor, the void fraction, and in this case the apparent permeability through the use of particle result simulations. The contents of this presentation is a brief introduction, the research questions, procedures, results, and conclusions. As is well known, an adequate description of the fluid dynamics in a wall-cooled packet reactor is essential to describe the performance of highly exothermic oxidation reactions. It is because the fluid dynamics governs the heat and mass transfer mechanism. Here, for that, considering the fluid dynamics in the modeling of the wall-cooled packet reactor can improve the prediction of the temperature profiles and have a better control of the hotspot. So, the proper design, control, or optimization requires the development of a reliable model describing properly fluid dynamics. For several decades, the fluid dynamics in the packet bed has been described by using pseudo-continuous modeling approaches. And the main approach have been considered Navier-Stokes equation coupled with the Darcy and Forchheimer. Here, the effective coefficients capture the main contribution of the solid and fluid phases. These coefficients are the void fraction and a term taking account the resistance by the solid presence. Here, the Darcy-Forchheimer is the most used. This term consider the Darcy permeability and the Forchheimer coefficients. These coefficients have been determined by using correlations, the well-known correlations declared, or empirical expressions. In the better of the cases, this empirical expression is fixed to pressure drop observations. And this leads to uncertainties on the coefficients. An alternative is the use of a new approach, taking account the pseudo-continuous simulations based on particle result simulations. Here we propose the use of Navier-Stokes equation with a D term that consider all solid resistances in the packet bed. Here the fluid dynamic descriptor are determined, the void fraction and the solid resistance in the D term are determined from particle result simulations and volume averaging method. And the question here is it possible to transfer information from the local scale to the pseudo-continuous scale to obtain an adequate description of the velocity profiles in a packet bed reactor? To answer these questions, we propose a study on the case of an industrial scale reactor where a selective oxidation reaction is carried out. We consider a tube with 2.5 centimeters of diameter and 2.6 meters of length, packed with CO2 in its annotated phase. We consider a spherical particle with 8.2 millimeters of diameter. This system is described in the pseudo-continual approach throughout the momentum equation, the continuity equation, and the Navier-Stokes equations. We consider here the epsilon has the void fraction has a function of the radial position, and this term describes the inertial of the fluid, the pressure drop, the viscous term, the dilatation of the fluid, and a D term that consider all resistances to due to the presence of the solid. We need to determine these coefficients from particle result simulations. We say all resistances due to the presence of the solid taken accounting in the D term are described by using Darcy term. Here, this term consider the apparent permeability. Tensor are the velocity, the superficial velocity. From analogy with the intrinsic pressure drop, we obtain these equations. We can now the intrinsic pressure drop, making use of the averaging theorem. We decompose the term in two terms: the volume average of the gradient pressure and all forces, all normal forces acting on the surfaces of the particle. With this, we obtain a definition of the apparent permeability in terms of the void fraction, the superficial velocity, average velocity, and the superficial and volumetric forces. We need to obtain these quantities from particle result simulation. For that, we propose a methodology. First, we consider a unit cell and we divide this cell in several annular cylinders. We can decompose in the solid and fluid phases and determine the volume average quantities. Due to the computational limitation, we need obtain a representative unit cell. For that, we carry out the artificial packing using rigid body method implemented on Blender software. We consider the same system, a tube with 2.54 centimeters and 1.5 meters of length, packed with pellets of 8.2 millimeters of diameter. After a visual analysis, we obtain, and after a visual analysis and comparing with the experimental packing, we obtain a unit cell of just 14 centimeters of length that represent the global structure of the packing, the experimental packing. In this cell, we solve the momentum equation considering Navier-Stokes equation for compressible flow, and we obtain the following. Here, to evaluate the adequacy of the particle arrangement, we compare the void fraction obtained from the unit cell with the obtained from Yuan using discrete element method in a similar packet, and the result obtained by Partapor and Dixon using the blended Python workflow. We observe the same strength in the void fraction as a function of the radial positions. Now, in order to evaluate the particle result simulations, the prediction of the pressure drop obtained from particle result simulations, accounting the compressible and incompressible assumptions, are compared with obtained by observation in experimental industrial wall-cooled packet reactor at different particle Reynolds number. Here, particle result simulations and counting for the fluid compressibility is the only approach describing properly experimental observation of pressure drop. Figure 3 display axial and radial slices of the velocity magnitude at different radial and axial positions. Two main regions we can observe in the figure, and the first maximum points located at the sun near to the wall, and the second maximum point near to the contact between the center and peripheral particles. These maximum points also can be observed in the axial slices. We can observe maximum points near to the wall and near to the contacts, the central contacts. These are zones with preferential path flow or channeling zones. Also, we can observe in these zones and the higher local void fraction located in these zones. And now, to evaluate the capability of the prediction of our pseudo-continuous model based on particle result simulations, we compare the velocity profiles as a function of the radial position with the obtained from average particle result simulations. Our model predict similar profiles along of the radial positions with the same values of the maximum points in the velocity. The maximum points are located in the same position that the void fraction reached its maximum. However, near to the wall, the effect of the non-slip boundary condition have a effect. Not how our methodology predict the resistances due to the presence of the solid and rest on an apparent permeability. Here, the apparent permeability obtained from particle result simulation using to carry out the simulations are compared with the H-field correlations. We observe several differences in the zones with high void fractions, but a similar trend along of the radial positions. On the other hand, the compressibility effect was studied in this work. For this, we compare the velocity profiles obtained from particle result simulations and considering compressible and incompressible flow at different particle Reynolds. We observe several differences in the zones with high void fraction. The higher difference are found near to the wall. In these zones, this difference are due to the high gradient present in the near to the wall zones. Followed with the compressibility effect, we show how the fluid is compressed and dilated throughout of the use of divergence of the velocity. Here, and the negative values represent the compression of the fluid, and values of the positive values represent the dilatation of or expansion of the fluid. comparing the A and B figure, we note how the fluid, the magnitude of the divergence of the velocity increase with the particle Reynolds increase. Also, we can observe zones with compression of the fluid from of the particle in the actual direction, and a dilatation of the fluid from in the posterior to the particle zone. As conclusion, we obtain a new pseudo-continuous model that uses local information from particle result simulations and a new formulation for the apparent permeability based on solid-fluid interfaces informations. This information allowed obtain a good description of the velocity profiles. Finally, the results obtained by evaluating the effect of the compressibility on fluid dynamics indicate the need to take in account in the modeling of a packet bed reactor. I would like to thank the following institution for the support. And thank you for your attention.
Many thanks, Alberto, for your very nice presentation. And the paper is now open for discussion. We have a couple of minutes. So if there is any question, please feel free to open your mic and turn on your camera and ask. No questions, no curiosities. So if this is the case, I would like to thank Alberto again for the very nice talk. And I would like to thank also all the speakers of this last session of the conference. I hope you have enjoyed this session on the advances in chemical reaction fundamentals. And I invite and encourage you to join the closing ceremony now.
Thank you very much, Mr. Chairman. So I think that we will start the official closing of the conference in a couple of minutes. Okay. Colleagues, finally we have finished all our presentations, all our activities at the ChemReactor 24 conference, I would like to start the closing of the conference. I prepared some presentation, but maybe first I will ask our colleagues from Milano Politecnico, Matteo and Giampiero and Enrico. Can you please say a few words about this conference and about your impressions of this conference, please?
Okay, I will start since my mic is switched on as far as I see. Well, I'm extremely satisfied. I'm extremely satisfied that the wishes I make at the beginning of the conference, having top level plenary lectures and keynote speakers, having very good quality presentations from also very young scientists, has become a reality. So I'm satisfied that this difficult Milano edition of ChemReactor, let me call it like that, has succeeded in keeping the quality, the historical quality of the ChemReactor conference series at this level. And let me also add that I'm quite satisfied to see that the chemical engineering community, and specifically the chemical reaction engineering community, is so alive. I see advanced methods and or conventional methods apply to the new challenges that this energy transition era is posing to all of us and specifically to our community. And I guess that this was a very good stage to show what the chemical reaction engineering community is doing in this field. So overall, again, thanks to all the attendees, to the plenary lecturers and to the keynote speakers. And again, thank you to you and all the people from Boresco for the organization level of the event.
Thank you.
Okay, so I can say a few words. So I fully agree with Giampiero, and I was very satisfied by the quality of the presentations, and in particular, as Giampiero already said, our community is a very lively community, and he will certainly have a prominent role in all the challenges that we have ahead in terms of energy transition, especially. So we have seen electrification coming into the game, both at the level of the reactor scale or electrocatalysis, and contamination with the catalysis as well. So I think it's a good hope also for all of us, for the young people, also to have a great future in our discipline. I also want to say a big thank you to Andrei and Tatiana. So we interact quite a lot together with Giampiero during these 2 years or 3 years almost. So it was a very, active interaction. I think we came along pretty well, and this actually is reflected also in the success of the conference. So thank you again for this opportunity.
Okay, thank you.
Just one word from my side. My colleagues who have been really involved in the organization of the conference have already said many things, and I would like just to add my congratulations to the whole organizing and scientific committee for a very successful and very interesting and stimulating conference. Let me just add that I was particularly impressed by the quality of the plenary lectures that you selected. My compliments, they have been extremely inspiring, and I'm sure that there will be follow-ups on their contributions. So again, I'm glad that Milano has been part of this very successful event, and I'm very grateful to our Russian friends and colleagues for the involvement of the Milano group in this activities. Thank you very much.
Thank you, Enrico. Okay, maybe I will now make presentations about some statistics of the conference and other related things. And afterwards, of course, everybody who will want to say a few words, you will have such an opportunity. So let me start. Just a minute. Okay, do you see my presentation? It's okay?
Yes.
Okay, so a few words about our conference, which has finished at the moment. First of all, just statistics. I should say that this conference was attended by 251 participants from 38 countries. Comparing this result with the previous CAM reactors, I should say it is a little bit unexpectedly, because we all made this conference in not very easy times, right? But I should say it's one of the best results during at least last 10 years, I think. So nevertheless, despite any difficulties, we have managed to make together, of course, such a conference with at least such a great attendance. You see the world map here, and the green color here shows the participants, the countries which participated in this conference. You see it seems that we already occupy. So the green color is at least half of the territory, yes, maybe. And we'll work more to expand this territory, of course. In general, we had 6 plenary and 6 keynote lectures, and I would like, and I'm also, like Enrico, want to say that the selection of lecturers, in my opinion, was brilliant, and really it was very interesting presentations. Of course, there were also very interesting oral and poster presentations. We have 130 orals and approximately 80 posters. And I should say here we have also significant expansion, because in our previous conferences during last 5 or 6 times at least, we have usually 80-85 oral presentations and 2 conference streams. In this conference, we have found that we have very many interesting contributions, and it's not easy to select something like 80 or 90. And so we decided to make 3 conference streams. It's, in my mind, it gave positive results. And finally, we have more oral presentations. Okay. I would like to thank, first of all, of course, our International Scientific Committee and its chairman, Valentin Parmon. So you see it's very representative organ, very representative committee. So the people who are really respected in our chemical engineering area and who did a lot for development of CAM reactor conference, of course. Regarding this conference, I would like to say thanks to our chairman, Alexander Noskov, Professor Alexander Noskov, and Professor Jean-Pierre Groppi. Thank you very much for chairing the conference and organizing team. I would like to mention Professor Matteo Maestri and Tatiana Zamulina. All these people made a great, huge work for preparation of this conference. And I should also would like to mention here the conference organization Ilias Company, who is our partner, CAM reactor partner for already 15 years. So of successful cooperation, collaboration. I would like to say gratitude to David Maharadze, the director of this company, and Yulia Zhartov, who also worked a lot on the organization of the conference. We have, it's a CAM reactor tradition that for each conference we select the program committee, because the selection of contribution is a very not easy process. So actually each abstract, each contribution is evaluated, at least those contributions for oral presentations are considered by at least 4 reviewers, sometimes 5 or 6 reviewers, to provide independent and objective evaluation of all contributions. And I should say that all people mentioned here, the people from Boreskov Institute of Catalysis and Milano Polytechnica, it's a joint, very effective, efficient team, which did really, it's not a joke, huge work on reading and evaluating, reviewing of all these contributions. I am very grateful to all these people for their very significant and big work. I would like to say thanks to local organizing committee from Politecnico di Milano, and also to the team which provided the technical support. You see that our conference was a little bit unusual for us. Not say a little bit, quite unusual for us, because we had online presentations and 3 parallel streams and so on. So every time in each stream we had some supervisor people. Mostly all these people are not special experts, they are also participants of the conference. They participate like researchers, but at the same time they were helping to arrange all technical side. It's people from Boreskov Institute, also from Institute of Solid State Chemistry here in Novosibirsk, from Ilya Mkharadze from Ilios, and actually we also had support from professional company Video Profi, who provided the all this work, including the simultaneous translation of all presentations, not only in Zoom but also to YouTube. And of course, I'm very grateful to the most important people in our conference, to our participants, the people without whom our conference is simply impossible. And in my mind, I have very positive, very bright impressions from the current conference. I see a lot of very interesting, very professional, very skilled people. And I also would like to support the impression that we are a very live community. That's right. It was very interesting, it was not interesting only from a scientific point of view, but it was also interesting to communicate. Okay, what we will do afterwards? A few words about the conference is completed but still we have something to do afterwards. First of all, among these post-conference issues, the first thing is, from one side, we had complicated task to make the conference online, but at the same time, it gives new opportunities. For example, we had YouTube translations of all presentations. And I should say that all these presentations will be kept and will be made available at YouTube for unlimited time. So you will have a chance, anybody will have a chance to, for example, if you have missed some presentations, something else, you can then get back and watch any moment of the conference. So all conference is recorded and we can get back and see it again if we will need this. So we will a little bit later, we will provide information about the references to YouTube. But to my knowledge, first time at least, it will be these players which were placed in the conference website, they will be kept at the same place, and so it will be possible to see this recording just through the YouTube references at the conference website. Of course, a very important question, a very important part for our conference is conference proceedings. And as usually, as traditionally, we have very good collaboration with a chemical engineering journal, which now is, seems to me, maybe #1 journal in chemical engineering in the world, or among very best journal at least. And so actually we are very proud of this collaboration. So again, in this case, we have an agreement to make a thematic issue dedicated to our conference. And I will just repeat the common rules. They are the same like in previous conferences. So there is a strong rule that only contribution presented at the conference, really presented, physically presented at the conference, will be considered for publication. Manuscripts, first of all, you should prepare the manuscripts, maybe in some preliminary form. But first, please send it to Tatiana Zamulina. You see the address here, conference secretary, for preliminary selection. So usually our program committee, we just look through the list of all these manuscripts, and we just to be sure that the quality of manuscripts is acceptable, and but usually it is acceptable in majority of cases. But also to be sure that the important question that the manuscript corresponds to the publication profile of this journal. So don't forget that it is an engineering journal mostly. Then authors of selected papers will receive an invitation to upload the manuscript to editorial system, as usually usual procedure, and all manuscripts will then undergo regular journal reviewing, so without any, let's say, discount. Yes. So I would like to ask the main problem. As a guest editor of this such special issues, I want to say that the main problem in preparation of such issues is problem how to find the reviewers, enough reviewers which will provide the review in necessary time and so on. Sometimes to collect 3 reviews, we have to invite sometimes 10, sometimes 12. So our record is 20 invitations to reviewers. So it is not easy, of course. It's a problem in all journals, as I know currently. So if you will receive the invitation to review some manuscripts in this thematic issue, please don't refuse, and please don't ignore the invitation for this reviewing. You will help all other participants. It doesn't mean that you are asked to give predominantly positive decision. No, you as a reviewer, you can make any decision you think it is necessary, but just don't refuse from reviewing, please. In this conference, we also, if somebody would like, we also have additional option, another one, a journal, Catalysis in Industry. It's also a journal which is indexed in Scopus. So if there people will decide to publish here, you're welcome as well. We consider the social part of any conference, and especially ChemReactor conference. The social part is very important, and we have many years of traditions that usually we have not only scientific communications at the conference, but we have a lot of personal communications. In my mind, it's quite seriously, this is one of the most important functions of conferences. So to provide the contact between people, including the contact on some social level, not only scientific. Unfortunately, in our case, we had no possibility to provide as usually the conference dinner. Nevertheless, yesterday we had some singing party and dancing party. And I should say, and yesterday I told, I just will repeat now, that we are going to make such joint, to create a joint song. So a little bit later, we will send you all the necessary instructions how to do it. In general, I can say that there is a text, there is a music, and there will be some example of how it is possible to sing this text with this music. And we will need to have your audio records how you sing this question and the song, and afterwards we will try to combine this in one track. And our aim is to make something like choir singing, of conference participants and with some preliminary brand singing conference. I think it will be interesting, and I don't know actually other chemical engineering conferences which had such experience. We will be maybe the first one here in this area. Okay, so we'll send all instructions, and possibly we'll place all necessary things at the conference website. The conference website will stay alive and will work for a long time more. Finishing my presentation, just to remind the list of chem reactors starting from chem reactor 13 in 1996, when it became international. Just meaning maybe this event included 2 participants from outside Russia, but you see the history, and the history, it seems to me, is very interesting. And of course, this is not the end of the history, and I would like to forward then my words to the hosts of the future Chem Reactor 25 conference. So please, Günther, are you here? I'd like to.
Yes, of course.
Hello. Please say a few. Yes.
So you see also the screen, the slide.
Mm-hmm.
Yeah. So from my side, I want to announce that the location of the next conference was decided to be Germany, and we still are about to find a well-suited location. It will be in the time window September to October 2023. The current local organizing group is Hans-Jörg Freund and Kai Olaf Hinrichsen and myself, and we will do our best to maintain the high quality of the conference, which will hopefully be a live conference then again. So let's not hope that the situation will stay similar to as it is currently. And also, but not exclusively, after having heard now the presentations of the last few days, we think it will be a good idea to keep on focusing on the consequences and the ideas of chemical engineers related to the new solutions which can be realized through the energy transition. Yeah, so I think this was very lively and interesting discussions about these new possibilities, which make it possible to move things onward, which have been maybe sticking for quite a while. Yeah, so I will be pleased to welcome you all in 2 years' time, approximately, in Germany. So, thank you.
Thank you very much, Günther. I should say that during few last chem reactors, maybe the one of the strong sides of chem reactor is that we are lucky. We had very good partners for organizing the conference. We have, like in this case, we have excellent partners in Milano Politecnica, and I'm very grateful to them. And seeing the proposed list of organizers of the next chem reactor event, I see we keep this tradition, and this collective looks excellent, and I hope it will be the great conference as well. Thank you, Günther. Okay, does anybody else want to say something? You have the possibility to do this right now.
Jan Kopczynski from Montreal, Canada. I would maybe like to also to say something. I was surprised. First of all, thank you for the nice conference organization and really the good talks. I was surprised that the chem reactor was never in North or South America or even in Asia. So I would like maybe to propose, if possible, to hold it in not 2023, maybe 2025, in 4 or 5 or 2026, maybe in North America, maybe in Canada, maybe in Mexico. If that is an option, and would be nice. I know we have also a strong team here in North and South America that would be, I guess, willing to host this conference after the German one. So I don't know if that is something. Keep an open mind, and we are all up for it. And yeah, I just want to throw it out there. If you're welcome, if you would like to travel over the Atlantic or the other side to the Asian countries, I think that is something we should keep in mind.
Mm. Yes, it's very, very, very correct. Very good proposition. Because we actually we're still inside Europe, and we are thinking for many, not many, but for a few last maybe 2 or 3 events, we already start thinking about some other territories, including of course USA, Canada, or Mexico. And it's very good that you initiated this discussion. So your proposal is already taken into account. Okay, so thank you very much. Thank you.
Yeah, you're welcome.
So all other people who want to propose also some other countries, territories, and so on, you're all welcome. Maybe now, maybe you can write afterwards if you like. So of course we are thinking about the future, about some future events. Yes.
Thank you.
Okay, it seems that all the words are told, are said. So thank you very much, all of you, again, and welcome at ChemReactor 25. See you. Bye-bye.
Bye, everybody. Thank you very much.
Thank you.
Thank you. Thank you, Andrei.
Thank you for everything.
Compliments.
Bye.
Bye.
you.